Billions of years ago, the universe held only a diffuse mix of gas, dust, and the faint traces of energy left over from the Big Bang. Somewhere within this seemingly endless expanse, a delicate balance of forces, gravity, pressure, and motion, started a chain reaction that would shape the very neighbourhood we now call home. From the smallest specks of dust to colossal spheres of gas and rock, these ingredients collided, stuck together, and spun, setting the stage for the formation of planets, moons, asteroids, and the sun itself. What began as emptiness became a dynamic, evolving system, a cosmic dance of matter and energy that eventually formed the intricate and harmonious structure we now recognise as the solar system. Before we delve into this journey, like the video and comment below where in the world you're watching from and what time it is there now. Now, settle in for a journey to the beginning of the solar system. Billions of years ago, long before humans walked the Earth or even before our planet itself existed, the universe was a vastly different place. The stars we see today were only beginning to form, galaxies were scattered and still taking shape, and the vast stretches of space were filled with a thin, almost invisible fog of gas and dust. It was in this quiet, seemingly empty stage of the cosmos that the story of our solar system began. A story that would take billions of years to unfold, and that still leaves traces in every corner of our cosmic neighbourhood. To truly understand how our solar system came to be, we need to look far back in time, to a period when nothing yet looked like the planets, moons and asteroids that now circle our sun, and when the raw materials of creation were slowly gathering under the invisible hand of gravity. The universe itself is about 13,800,000,000 years old, and for the first several billion years it was a place of simplicity and emptiness. The remnants of the Big Bang, the great expansion that brought space, time and energy into being, were still cooling and spreading out. Hydrogen and helium, the lightest and most abundant elements, floated freely in enormous clouds called nebulae. These clouds were like cosmic oceans, vast and nearly imperceptible in their density, stretching across light years of space. Within these clouds, tiny variations in density began to appear, influenced by the gentle tug of gravity. Where the cloud was just a little denser than the surrounding space, gravity began to pull more material toward that spot. Slowly, over millions of years, these dense regions grew even denser, creating the seeds for the stars and planetary systems that would follow. The process that led to the formation of our solar system began in one such cloud, a giant molecular cloud composed mostly of hydrogen gas, with smaller amounts of helium, dust, and traces of other elements like carbon, oxygen, and iron. This cloud was cold, with temperatures near -273 degrees Celsius, just barely above absolute zero. The dust within it, tiny particles smaller than a grain of sand, was crucial because it helped the gas cool and clump together. Over time, a disturbance, perhaps a shock wave from a nearby exploding star called a supernova, compressed part of this cloud. This compression increased the density of the gas and dust and caused it to collapse under its own gravity. What began as a gentle gathering of particles soon became a rapid implosion, drawing in more and more material, and in the centre of this collapsing cloud, the first spark of our sun was about to ignite. As the cloud collapsed, it naturally began to spin. This rotation was initially slow, almost imperceptible, but as more material fell inward, the spinning increased, just like a figure skater pulling in their arms to spin faster. The spinning cloud flattened into a wide, thin disk, with most of the mass concentrated at the centre. This disk, now called the Protoplanetary disk, became the stage for the drama of planetary formation. The central mass continued to collapse, becoming hotter and denser until it reached a point where nuclear reactions could begin. At this moment, approximately 4,600,000,000 years ago, the Sun was born. In its core, hydrogen atoms fused into helium, releasing enormous amounts of energy and creating the light and heat that would one day make life possible on Earth. While the Sun was forming, the material in the surrounding disk was not idle. Small particles of dust and ice began to stick together through a process called accretion. Tiny grains collided and stuck, forming larger clumps, which in turn collided with other clumps to form even bigger bodies called planetesimals. These were the building blocks of planets. Some planetesimals remained small, becoming asteroids or comets, while others grew large enough to attract more material with their gravity, eventually forming the planets we know today. The inner part of the disk, closer to the hot young sun, was too warm for ice to survive. Here, rocky materials dominated, giving rise to the terrestrial planets: Mercury, Venus, Earth, and Mars. Farther out, where temperatures were lower, ices could condense, allowing the gas giants, Jupiter, Saturn, Uranus, and Neptune, to grow massive and capture thick atmospheres of hydrogen and helium. The young solar system was a violent and chaotic place. Collisions between planetesimals were frequent and often catastrophic. Some bodies were shattered into pieces, contributing to the belts of asteroids and comets that still exist today. Others merged to form larger planets. Evidence from meteorites, which are fragments of ancient bodies that have fallen to Earth, suggests that this process was intense and lasted for tens of millions of years. During this time, the planets did not have the stable, circular orbits we see today. Their paths around the Sun were erratic, shaped by gravitational interactions with other bodies and the residual gas in the disk. Some planets moved inward, others outward, and some were ejected from the solar system entirely. This early era, sometimes called the period of planetary migration, helped sculpt the solar system into the arrangement we recognize now. Water and organic molecules, essential ingredients for life, also have their origins in this early solar system. In the colder outer regions of the disk, icy planetesimals formed, capturing water, carbon compounds, and other volatiles. Some of these bodies eventually collided with the young Earth, delivering water and possibly the basic building blocks of life. This is why comets and certain types of asteroids are so interesting to scientists today. They are like frozen time capsules, preserving materials from the dawn of the solar system. By studying them, we gain insights into the conditions that existed over 4 billion years ago, before Earth even had oceans or continents. The formation of the Moon is another key chapter in the solar system's early story. Current evidence suggests that a Mars-sized body collided with the young Earth about 4,450,000,000 years ago. The impact was so powerful that it ejected vast amounts of material into orbit around Earth. Over time, this material coalesced to form the Moon. This event not only created our natural satellite, but also influenced the Earth's rotation and tilt, helping to stabilize the planet's climate over billions of years. Without this dramatic collision, life on Earth might have evolved very differently, or perhaps not at all. Even as the planets grew, the Sun continued to emit strong solar winds, streams of charged particles moving outward at incredible speeds. These winds blew away the remaining gas in the disk, ending the era of planet formation and leaving behind a cleaner, more stable solar system. What remained were planets, moons, asteroids, comets, and smaller debris that continue to orbit the Sun in delicate gravitational balance. The asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, and the distant Oort cloud are all remnants of this formative era, frozen records of processes that occurred billions of years ago. One of the most fascinating aspects of the solar system's formation is that it is not unique. Astronomers have discovered thousands of other stars with disks of gas and dust, many of which are forming planets today. By comparing these distant systems to our own, scientists can better understand the events that shape the Sun and its planets. Observations from powerful telescopes, both on Earth and in space, allow us to witness similar processes occurring around other stars, providing a living laboratory for the story that began in our own cosmic backyard. Our understanding of the solar system's origins has grown immensely over the past century. Early astronomers could only speculate about how the planets came to be. With the advent of modern telescopes, spectroscopy, and space exploration, we now have a detailed picture of the forces and processes involved. Meteorites provide chemical fingerprints of the early solar system. Space missions to comets, asteroids, and planets allow us to see firsthand the variety and complexity of these objects. Computer simulations recreate the dynamics of planet formation, showing how gravity, collisions, and migration shape planetary systems over millions of years. Each piece of evidence builds a more complete picture, revealing a solar system that is at once orderly and chaotic, beautiful and violent, simple and complex. The story of the solar system's birth is also a story of time, immense, almost incomprehensible time. From the collapse of a cold cloud of gas and dust to the formation of a hot glowing sun and the planets that orbit it, billions of years of slow, patient processes have gone into shaping the environment we inhabit today. Each planet, each moon, each asteroid and each comet carries a memory of that time, a story written in its composition, orbit, and surface features. The Earth itself, with its oceans, continents, and atmosphere, is a direct product of these ancient events, the culmination of countless interactions and collisions that began in the quiet depths of space long before life existed. As we study the solar system, we also gain a deeper understanding of our place in the universe. We see that our Sun is just one of hundreds of billions of stars in the Milky Way galaxy, which itself is one of hundreds of billions of galaxies in the observable universe. Yet despite this vastness, the processes that shaped our solar system are universal. Gravity pulls gas and dust together, collisions build larger bodies, and over time planets form. This realization connects us to the broader cosmos, reminding us that the Earth and all its inhabitants are products of the same forces that have shaped stars, galaxies, and planetary systems across the universe. The origins of the solar system are not only a scientific curiosity, but also a profound story of creation, transformation, and interconnectedness. They teach us about the laws of nature, the flow of time, and the delicate balance of forces that make life possible. By studying the solar system's beginnings, we also prepare to understand its future. The planets will continue to move, the sun will evolve, and over billions of years our solar neighborhood will change in ways we can only begin to imagine. Yet, the traces of its formation will remain, a testament to the processes that brought order out of chaos and created the world we know today. From a diffuse cloud of gas and dust, from tiny variations in density amplified by gravity, from countless collisions and near misses, from the quiet patience of cosmic forces the solar system emerged. It began with nothing but simple elements, slowly shaped by energy, motion, and gravity into the intricate system of planets, moons, and smaller bodies that orbit the sun today. Understanding this story is not just about understanding the past, it is about connecting to the vast, ongoing process of creation in the universe. Each star forming in a distant galaxy, each planet coalescing from dust, each comet hurtling through space, continues the story that began billions of years ago in a cold, quiet corner of our galaxy. A story that eventually led to our Earth, our life, and our capacity to look back and wonder at the stars. The concept of nothing is one of the most fascinating and difficult ideas for humans to grasp. When we speak of nothing, we're not simply talking about empty space in the ordinary sense, like the emptiness between furniture in a room. We're talking about a deeper kind of nothingness, a state before anything existed as we know it, a kind of emptiness that existed before the planets, stars, and galaxies filled the cosmos with light and matter. Understanding this idea is crucial because it helps us explore the conditions that eventually led to the formation of our solar system, the small neighborhood of the universe that we now call home. To truly appreciate this story, we need to start by trying to picture what nothing in space really means. Before the solar system existed, long before the Earth, the Sun, or even the distant planets we now know, the universe was in a very different state. It was not empty in the way we might think. It did not have neatly arranged planets or shining stars. Instead, it consisted of a vast, diffuse mixture of gas, dust, and faint traces of energy. These materials were spread out across enormous distances, almost uniformly, and were extremely thin. They were the leftovers from events that happened billions of years before the first humans walked the Earth. To get a clearer sense of the timeline, consider that our solar system itself formed about 4,500 million years ago, which is more than 4.5 billion years before today. Yet, even before that, the universe had already existed for around 9 billion years, quietly expanding and evolving. The emptiness that existed before the solar system was not truly empty in the sense of being a perfect void. It was a near vacuum, almost nothing, but still filled with tiny amounts of particles and energy. Scientists often describe this state as a cosmic gas cloud, a sprawling nebula that extends across unimaginable distances. This pre-existing material was primarily made of hydrogen and helium, the two lightest elements in the universe. These elements formed shortly after the Big Bang, which occurred approximately 13,800,000,000 years ago. In the moments after this enormous explosion of energy and matter, the universe began to cool down, allowing the first atoms to form. Hydrogen atoms, the simplest and most abundant type, were everywhere, with helium atoms sprinkled throughout. There were also trace amounts of lithium and other very light elements. But for the most part, space was an almost featureless expanse, dominated by these simplest building blocks of matter. This vast emptiness had certain hidden properties. Although it seemed calm and static, it was actually dynamic and restless. Gravity, the invisible force that pulls all matter together, was constantly at work, slowly tugging these atoms toward each other. Even in such diffuse conditions, tiny fluctuations in density, small regions where matter was slightly more concentrated than the surroundings, began to appear. These fluctuations were incredibly subtle, almost imperceptible, but they were crucial. They were the seeds from which stars, planets, and galaxies would eventually grow. The fact that such tiny irregularities could lead to the creation of entire solar systems is one of the most remarkable aspects of cosmic evolution. Before the solar system, the universe was also filled with radiation, the faint glow of energy that had travelled across space since the earliest moments of the Big Bang. This energy, now observed as the cosmic microwave background, pervaded the universe and provided a kind of cosmic backdrop. While we might call it empty space, it was actually alive with this lingering energy, a quiet reminder of the universe's fiery beginnings. This radiation was not visible to the human eye, and it carried very little heat by the time the universe reached the age when our solar system could form, but it was still a fundamental part of the cosmic environment. At this point, it is important to recognize that nothing in space does not mean the absence of physical laws. Even in the emptier stretches of space, the forces that govern matter and energy were already at work. Gravity, as mentioned, was pulling matter together. Pressure and thermal motions caused particles to move and interact in subtle ways. Magnetic fields existed, shaping the behavior of charged particles. The laws of physics, those rules that dictate how matter and energy behave, were fully operational, even in the most seemingly empty regions of the cosmos. This means that nothing is not an absence of rules, but rather an absence of large-scale structures. The universe had not yet formed stars, planets, or complex chemistry, but it was far from chaotic. It was orderly, governed by universal laws, and full of potential for future creation. The emptiness that existed before our solar system can also be thought of as a stage, waiting for the performance to begin. In a way, it was a blank canvas, stretched across billions of light years, ready to host the complex dance of matter that would eventually give rise to stars and planets. The pre-existing conditions, the distribution of hydrogen and helium, the slight irregularities in density, the lingering energy of the early universe, were all part of this cosmic canvas. Without them, the solar system, and indeed all planetary systems, could never have formed. The initial state of emptiness was therefore not meaningless. It was pregnant with potential, containing within it the blueprint for everything that would come later. Over time, these tiny irregularities in the cosmic gas clouds began to grow. Gravity, which is weak on small scales but powerful over vast distances, slowly pulled hydrogen and helium together into larger clumps. As these clumps grew denser, they began to attract even more matter, gradually forming massive clouds of gas and dust. Some of these clouds were incredibly large, stretching for hundreds of light years, while others were smaller pockets within the larger structures. The interaction between gravity and the pressure of the gas created waves and motions within these clouds, stirring them like a cosmic cauldron. Even in what appeared to be empty space, there was movement, tension, and transformation, happening at a level far beyond ordinary human experience. These pre-existing conditions, the seemingly empty spaces and the diffuse clouds of gas, were also influenced by past cosmic events. Supernovae, the explosive deaths of the first generations of massive stars, had already occurred in some regions. These explosions scattered heavier elements, like carbon, oxygen, and iron, into the surrounding space. While hydrogen and helium were the main ingredients, these trace elements were vital for later stages of planet formation. They would eventually become the building blocks of rocky planets, the cores of gas giants, and even the elements necessary for life. In this sense, the emptiness of space before the solar system was not uniform. It carried the memory of earlier cosmic history, a subtle richness hidden within its apparent void. As these processes continued over millions of years, certain regions of the cosmic cloud became increasingly dense. When the density reached a critical threshold, these regions began to collapse under their own gravity, forming the earliest protostars. This process marks the transition from nothing to something, the creation of the first seeds of stars within our part of the galaxy. Around these forming stars, the leftover gas and dust began to flatten into disks, spinning slowly due to conservation of angular momentum. These disks are known as protoplanetary disks, and they are the direct ancestors of the planets in our solar system. From the almost featureless emptiness, matter was now organizing itself into recognizable structures, guided by the invisible hand of physics. It is important to note that the scale of this transition is almost unimaginable. The emptiness of space, measured across light years, is vast beyond comprehension. 1 light year, the distance light travels in 1 year, is nearly 6 trillion miles. Yet the clouds that gave birth to our solar system spanned dozens or even hundreds of such distances. The transition from diffuse gas to structured star systems is not instant. It takes millions of years for gravity and motion to transform emptiness into organized matter. When we speak of the nothing that existed before the solar system, we are speaking of a dynamic, ever-changing emptiness, not a static void. It was a time of slow but inexorable creation, where the laws of physics sculpted the raw materials of the universe into complex forms. Another intriguing aspect of this pre-solar system emptiness is that it highlights the role of time itself. Without billions of years of gradual evolution, the tiny fluctuations in density would never have grown large enough to form stars and planets. Time allowed the gentle forces of gravity, motion, and pressure to act over unimaginable scales, transforming a near nothing into a highly structured cosmos. In this sense, nothingness is not merely the absence of things. It is a stage for processes, a backdrop for events, and a canvas for the slow artistry of the universe. The story of the solar system begins not with a sudden spark, but with patience, subtlety, and the persistent influence of fundamental forces over billions of years. Thinking about nothing in space also challenges our human intuition. We tend to imagine emptiness as a simple, easy-to-understand concept, but cosmic nothingness is profoundly complex. It is shaped by the tiniest particles, the faintest energy, the slowest forces, and the longest stretches of time. It is a kind of invisible richness, filled with possibilities that we cannot directly see, but can infer through careful observation and scientific reasoning. By studying this emptiness, astronomers and cosmologists can trace the history of matter, energy, and motion, leading to a deeper understanding of how our solar system, our planet, and ultimately ourselves came into existence. The story of the universe's beginning is both breathtaking and deeply mysterious, a tale that stretches our imagination to the very limits of time and space. To understand how the universe came into being, we must start at a moment that is far beyond the reach of ordinary human experience, a time so ancient that it defies simple comprehension. This was the moment that scientists call the Big Bang, a name that, despite its simplicity, represents an event of unimaginable energy and creation. Around 13,800,000,000 years ago, nearly 14 billion years before today, the universe began as an infinitely small, infinitely hot, and unimaginably dense point, a singularity that contained within it all the energy and matter that would eventually give rise to galaxies, stars, planets, and life itself. It is difficult for the human mind to truly picture such a state, for everything we know about space, matter, and time as we experience it did not exist before this point. Space itself, along with time, energy, and matter, emerged from this singularity, expanding and evolving into the vast cosmos we observe today. In the first tiny fractions of a second after the Big Bang, the universe underwent a period of extraordinary growth and transformation. During what physicists call the Planck era, which lasted only 1/100th of a trillionth of a second, the known laws of physics as we understand them break down, and the forces of nature were unified in a single extraordinary field. In these earliest moments, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were not yet distinct. But as the universe expanded and cooled, these forces gradually separated, setting the stage for the complex interactions that would govern the formation of matter and the behavior of energy for billions of years to come. As the universe continued to expand, it cooled just enough for the next stages of cosmic evolution to unfold. Within the first few minutes, temperatures fell from the unimaginably hot extremes of billions of degrees to a few billion degrees, allowing for the formation of the first atomic nuclei in a process known as nucleosynthesis. During this critical period, the universe produced the simplest and most fundamental building blocks of matter. Hydrogen, the lightest and most abundant element, came into existence alongside its heavier sibling, helium. A tiny trace of lithium, a rare and fragile element, was also formed. These light elements, created in the first 3 minutes of the universe, would later become the essential ingredients for stars, galaxies, and ultimately planets. Without this early alchemy of the cosmos, the universe as we know it would never have materialized. For the next several 100,000 years, the universe remained a hot, dense, and opaque sea of particles. Electrons, protons, and photons, particles of light, were locked in an intricate dance, constantly scattering off one another in a chaotic frenzy. The universe was a glowing, radiant fog, too dense for light to travel freely. During this period, the energy of the universe dominated its behavior, and the matter that would later coalesce into stars and galaxies could not yet form visible structures. It was only when the universe had cooled to around 3,000 degrees above absolute zero, roughly 380,000 years after the Big Bang, that electrons could finally combine with atomic nuclei to form neutral atoms. This epoch, known as recombination, allowed light to travel freely for the first time, creating what we now observe as the cosmic microwave background, a faint afterglow of the universe's fiery birth. The discovery of this afterglow in the year 1965 by Arno Penzias and Robert Wilson provided one of the most compelling pieces of evidence that the universe indeed began in a hot, dense state. As the universe expanded further, matter began to slowly clump together under the force of gravity, forming the first seeds of cosmic structure. Tiny irregularities in the distribution of matter, known as density fluctuations, allowed regions of slightly higher density to attract more matter, gradually growing larger over millions of years. These primordial clumps of gas, composed almost entirely of hydrogen and helium, were the first cosmic nurseries, the birthplaces of stars. As these clouds collapsed under gravity, the temperature and pressure at their cores increased, eventually igniting nuclear fusion and giving rise to the first generation of stars. These stars were massive, burning hot and bright, and they lived fast and died young, exploding as supernova and scattering heavier elements into the surrounding space. These explosions created the heavier chemical elements, such as carbon, oxygen, and iron, which are essential for the formation of planets and, ultimately, life. Over billions of years, the universe evolved from these first stars into vast collections of galaxies, each containing billions of stars, along with gas, dust, and dark matter. Galaxies collided and merged, triggering new waves of star formation and spreading the elements forged in stellar cores across the cosmos. Within these galaxies, clouds of gas and dust collapsed to form new generations of stars, many surrounded by disks of material that would coalesce into planets, moons, and other celestial objects. This ongoing cycle of star birth and death gradually enriched the universe with the chemical diversity needed to create planets like our own Earth. The story of the universe, therefore, is not simply one of empty space, but a dynamic, evolving tapestry in which matter is constantly recycled, transformed, and reshaped by the fundamental forces of nature. The formation of stars and planets depended not only on the presence of these chemical elements, but also on the delicate balance of forces within collapsing clouds of gas and dust. Gravity, the force that pulls matter together, competed with pressure, heat, and magnetic fields, creating a complex interplay that determined whether a cloud would fragment into multiple stars or form a single massive star. In the disks of material surrounding young stars, collisions and accretion gradually built larger bodies, from tiny grains of dust to planetesimals, and eventually to full-fledged planets. From tiny grains of dust to planetesimals, and eventually to full-fledged planets. Over tens of millions of years, these processes created planetary systems with remarkable diversity, ranging from small rocky worlds like Mercury and Mars to massive gas giants like Jupiter and Saturn. Each star and planet carries within it the legacy of the universe's earliest moments, the primordial ingredients forged in the first few minutes after the Big Bang. The Earth, along with the other planets in our solar system, is a direct product of this cosmic evolution. Around 4,600,000,000 years ago, in a quiet corner of a spiral galaxy we now call the Milky Way, a cloud of gas and dust collapsed to form the Sun. Around this newborn star, the remaining material coalesced into planets, moons, asteroids, and comets. The chemical elements produced by earlier generations of stars scattered across the galaxy by supernova were incorporated into these planets, providing the raw materials for geology, atmosphere, and life itself. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all forged in the hearts of stars that lived and died long before the Earth existed. In this way, the story of the Big Bang is intimately connected to the story of our own existence. Understanding the Big Bang and the early universe also requires grappling with some of the deepest mysteries of physics: dark matter and dark energy, two invisible components that dominate the universe, played crucial roles in shaping its evolution. Dark matter, which interacts through gravity but not through light, provided the scaffolding upon which galaxies and clusters of galaxies formed. Without dark matter, the universe might have remained a diffuse, structureless expanse of gas and radiation. Dark energy, a mysterious force driving the accelerated expansion of the universe, continues to shape its destiny, stretching space at an ever-increasing rate. While these components remain invisible and enigmatic, their influence is essential to understanding the large-scale structure of the cosmos and the conditions that allowed stars and planets to form. In the billions of years following the Big Bang, the universe continued to evolve, giving rise to galaxies of every shape and size, star clusters, and intricate cosmic webs of matter. Supernovae continued to enrich interstellar space with heavy elements, enabling the formation of planets with complex chemistry. The cosmic dance of creation, destruction, and recycling continued unabated, producing the conditions necessary for the emergence of habitable worlds. Within this grand cosmic narrative, the Sun and its planetary system emerged as a relatively modest but extraordinary corner of the universe, a testament to the power of gravity, nuclear fusion, and the laws of physics that govern matter and energy. The story of the universe's birth is not only a tale of matter and energy, but also a profound reflection on the nature of time, space, and existence itself. From the singularity of the Big Bang to the formation of stars, galaxies, and planets, the cosmos has been shaped by a combination of chance and necessity, order and chaos. Every atom in our bodies, every grain of sand on Earth, every photon of a light that reaches our eyes carries a history that stretches back to the earliest moments of the universe. By studying the cosmic microwave background, the distribution of galaxies, and the chemical composition of stars, scientists continue to unravel the mysteries of how the universe came to be, how the raw materials for stars and planets were forged, and how these processes set the stage for life itself. The story of the creation of elements in the universe is one of the most fascinating and awe-inspiring tales in all of science. It is a story that takes us from the tiniest particles of matter to the vast and luminous stars scattered across the cosmos. While hydrogen and helium are the simplest and most abundant elements, making up nearly all the matter immediately after the Big Bang, they are only the beginning. The more complex elements, the ones that make up our bodies, our planet, and everything around us, were not forged in the quiet emptiness of space. Instead, they were born in the blazing hearts of stars through a process known as stellar nucleosynthesis, a term that essentially means the building of new atomic nuclei inside stars. This process is the cosmic workshop where elements such as carbon, oxygen, nitrogen, and even iron are created, and it is also the ultimate source of the material that would eventually form planets and life itself. In the earliest moments of the universe, about 13,800,000,000 years ago, the universe was a hot, dense, and expanding fireball. In the first few minutes, protons and neutrons collided to form the very first atomic nuclei. This primordial period created mostly hydrogen, the simplest element, with just a tiny amount of helium and trace amounts of lithium. But these first elements were only the beginning. For all the more complex elements, the ones that make up the Earth, the seas, the air, and every living organism, another, much more extraordinary process would have to take place. That process required stars. Stars are colossal spheres of gas, mostly hydrogen, held together by gravity. At their cores, where pressures reach unimaginable levels and temperatures soar to millions of degrees, nuclear reactions occur. These reactions are the engines of the stars and the birthplace of new elements. Hydrogen nuclei, which are single protons, collide with enough force to overcome their natural electric repulsion and fuse together. This process is called nuclear fusion, and it releases vast amounts of energy in the form of heat and light, which is why stars shine. But hydrogen fusion is only the first chapter in a star's story. As a star ages, it begins to fuse heavier and heavier elements. In stars like our Sun, hydrogen fuses into helium, a process that can last billions of years. Once the hydrogen in the core is used up, the star begins to fuse helium into even heavier elements. The creation of elements heavier than helium, starting with carbon, is a delicate and complex process. Helium nuclei, also known as alpha particles, can collide under the extreme pressures and temperatures in the cores of stars. When three helium nuclei fuse together, they create a carbon nucleus. This process is known as the triple alpha process, a remarkable chain of events in which three tiny particles come together to form a new and more complex element. Carbon in turn can fuse with helium to create oxygen, one of the most essential elements for life. This means that both carbon and oxygen, the building blocks of life on Earth, owe their existence to the hearts of stars that lived and died long before our solar system formed. As stars grow more massive, their cores become even hotter, allowing them to fuse heavier elements. In these massive stars, a kind of cosmic alchemy occurs. Hydrogen fuses into helium, helium into carbon and oxygen, carbon into neon, neon into magnesium, and so on, all the way up to iron. Each stage of fusion releases energy that supports the star against the crushing force of gravity. But the fusion of iron is a special case. Iron is a stable element, and fusing it into heavier elements actually consumes energy rather than releasing it. This sets the stage for some of the most dramatic events in the cosmos, the deaths of massive stars in spectacular explosions called supernovae. Supernovae are among the most energetic and awe-inspiring events in the universe. When a massive star exhausts its nuclear fuel, it can no longer hold itself up against gravity, and its core collapses in a fraction of a second. The outer layers of the star are violently expelled into space, and temperatures and pressures reach levels far beyond what is possible in normal stellar cores. In this explosive crucible, elements heavier than iron, such as gold, silver, uranium, and lead, are created in a process known as rapid neutron capture, or the R process. These elements, forged in the heat and fury of a dying star, are then scattered across the cosmos, seeding future generations of stars, planets, and eventually life itself. The birth of elements through stellar nucleosynthesis is not a mere historical curiosity. It is a story that directly connects us to the cosmos. Every atom of carbon in our bodies, every atom of oxygen we breathe, and every atom of calcium in our bones was once part of the interior of a star. Some of these stars lived for millions of years, burning brightly before dying in cataclysmic explosions. The atoms forged in these stars travelled through space, sometimes for billions of years, before being incorporated into new stars, planets, and eventually living organisms. In this sense, we are not separate from the cosmos. We are literally made of stardust, a phrase that captures the poetic truth behind the scientific story. Stellar nucleosynthesis also explains the chemical diversity of the universe. Not all stars are alike. Stars vary in mass, composition, and lifespan, and these differences determine which elements they can produce. Small stars with masses similar to or less than that of the Sun live for billions of years and mainly produce helium and carbon. Massive stars, which may be tens of times heavier than the Sun, burn hotter and faster, creating a wider array of elements up to iron and eventually exploding as supernovae to produce even heavier elements. This variety of stellar processes ensures that the universe is chemically rich and diverse, capable of forming planets, atmospheres, oceans, and the complex chemistry necessary for life. Even the relative abundance of elements in the universe can be traced back to stellar nucleosynthesis. Hydrogen remains the most abundant element, followed by helium, and then oxygen, carbon, neon, and iron. These elements dominate the composition of stars and planets. The abundance patterns we observe today, in the Sun, in Earth's crust, and in distant galaxies, reflect the cumulative history of countless generations of stars, each one contributing its unique chemical fingerprint to the cosmic mix. By studying these patterns, scientists can reconstruct the life cycles of stars, the history of galaxies, and even the evolution of the universe itself. The creation of heavier elements is also a story of cycles and continuity. Stars are born from clouds of gas and dust enriched by previous generations of stars. They live out their lifetimes, forging new elements in their cores, and then return much of this material to space through stellar winds, planetary nebulae, or supernova explosions. This material becomes the raw ingredients for new stars and planets. In this way, the universe recycles its matter, constantly renewing itself, building complexity, and creating the conditions for planets and life to emerge. Each star is both a product of earlier stars and a potential creator of future generations, an ongoing chain of creation that stretches across billions of years. Observations of the universe confirm this story. Astronomers use powerful telescopes to study the light from distant stars and galaxies. The light carries information about the elements present in these objects. Spectroscopy, the study of the spectrum of light, reveals the chemical fingerprints of elements such as hydrogen, helium, carbon, oxygen, and iron. By analysing these fingerprints, scientists have discovered that the universe has become gradually more enriched with heavier elements over billions of years. This enrichment mirrors the life cycles of stars. The longer the universe ages, the more generations of stars have lived and died, and the more elements have been synthesized and spread across space. Stellar nucleosynthesis also has profound implications for our understanding of the origin of the solar system and life on Earth. About 4,600,000,000 years ago, in a quiet corner of the Milky Way galaxy, a cloud of gas and dust collapsed under its own gravity to form the Sun and the surrounding planets. This cloud was already enriched with elements created by earlier generations of stars, including carbon, oxygen, nitrogen, silicon, and iron. These elements came from stars that had lived, shone, and died long before the Sun was born. Without the preceding generations of stars, the solar system as we know it, with its rocky planets, oceans, and living beings, would not exist. The Earth itself is a direct product of stellar alchemy, a planet built from the ashes of long-dead stars. Even the smallest details of life trace back to stellar nucleosynthesis. The carbon in DNA, the oxygen we breathe, the calcium in bones, and the iron in our blood all owe their existence to the nuclear reactions inside stars. Life itself is thus a continuation of the universe's ongoing experiment in complexity and organization. Without the chemical elements forged in stars, the universe would remain a vast, empty expanse of hydrogen and helium, with no planets, no chemistry, and no life. The story of stars creating elements is therefore also the story of how the universe became capable of supporting life, a story that stretches from the hearts of ancient stars to every living being on Earth today. Furthermore, the study of stellar nucleosynthesis is not only about understanding the past, it is also a tool for exploring the universe's future. By examining the chemical compositions of stars, astronomers can predict their evolution, estimate their lifetimes, and anticipate the types of elements they will produce. This knowledge helps us understand how galaxies evolve, how new stars are born, and how the universe gradually becomes more chemically complex. In the far future, billions of years from now, stars will continue to forge elements, some of which may be scattered across space to form new solar systems, planets, and perhaps life. the cycle of creation continues, unbroken and timeless. Over 13 billion years ago, long before the first stars had flickered to life and long before galaxies had taken their grand, spiraling shapes, the universe was a place of astonishing simplicity and astonishing potential. In those earliest moments, just fractions of a second after the event we call the Big Bang, the universe was a hot, dense, and almost unimaginably energetic soup. In this primordial fire, the seeds of everything we see today, planets, stars, galaxies, and even ourselves, were quietly taking shape. Among the first and most important of these seeds were two remarkable elements, hydrogen and helium. These two elements, humble in their simplicity yet powerful in their abundance, became the foundation for the cosmic story that would unfold over billions of years. Understanding how hydrogen and helium formed not only illuminates the earliest moments of our universe, but also reveals the remarkable processes that have shaped every star, planet, and particle of matter we know. In the first few moments after the Big Bang, the universe was extraordinarily hot, dense, and turbulent. Temperatures reached values far beyond human comprehension, tens of billions of degrees or even more, and energy existed in forms we can scarcely imagine. In these conditions, ordinary matter as we know it could not exist. There were no atoms, no stable particles in the sense that we recognize today. Instead, the universe was filled with a plasma of fundamental particles, quarks, electrons, neutrinos, photons, and other exotic particles that moved at nearly the speed of light. The forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces, were beginning to separate and behave in the distinct ways that we observe in the modern universe. During this early epoch, the universe was expanding at a phenomenal rate, stretching space itself and cooling as it did so. In the first tiny fractions of a second, quarks began to combine, forming protons and neutrons, the building blocks of atomic nuclei. This process, known as nucleosynthesis, sets the stage for the formation of the simplest elements. By the time the universe was about 1 second old, the quark gluon plasma that had filled all of space had cooled enough for protons and neutrons to emerge as stable particles. These protons and neutrons were the raw materials from which hydrogen and helium would eventually form. Protons, being positively charged, would later become the nuclei of hydrogen atoms, the simplest of all elements, containing just one proton. Neutrons, neutral in charge, played a crucial role in helping form helium and other light elements, acting as essential companions in nuclear reactions. Over the next few minutes, as the universe continued to expand and cool to temperatures of roughly 1 billion degrees, protons and neutrons began to collide and stick together in a series of nuclear reactions. These reactions, collectively known as Big Bang nucleosynthesis, were responsible for creating the first atomic nuclei beyond the individual protons and neutrons. Hydrogen, the simplest element, emerged in astonishing abundance. The most common form, known as protium, consists of a single proton and no neutrons, representing the barest and most elemental building block of matter. Hydrogen's simplicity belies its cosmic importance. It became the most abundant element in the universe, accounting for roughly 75% of the normal matter produced in the aftermath of the Big Bang. Without hydrogen, stars could never ignite, galaxies could never form, and the vast cosmic web of matter would never take shape. But hydrogen did not form alone. In the same nuclear furnace, some protons joined with neutrons to create helium, the second simplest element. Helium has a nucleus composed of 2 protons and usually 2 neutrons, giving it a stability and mass slightly greater than hydrogen. Though far less abundant than hydrogen, helium still represented about 25% of the ordinary matter in the universe, a substantial quantity that would play a vital role in the formation of stars and galaxies. The process of helium formation was a delicate balancing act. Free neutrons, left to their own devices, are unstable and decay with a half-life of roughly 10 minutes. This meant that the window of opportunity for neutrons to combine with protons and form helium nuclei was extremely short. Yet, in those first 3 minutes of the universe, conditions were just right. Protons and neutrons collided in precisely the right ways, producing helium-4 nuclei, the most common and stable isotope of helium. This synthesis was efficient but limited, leaving vast quantities of hydrogen untouched, which would later fuel the formation of stars and galaxies. A tiny fraction of other light elements such as deuterium, tritium and lithium also formed during this period, but hydrogen and helium overwhelmingly dominated the universe, shaping the chemical canvas for everything that followed. The abundance of hydrogen and helium had profound consequences for the universe's evolution. In the absence of heavier elements, the first cosmic structures had to form from these simple elements alone. Hydrogen, with its single proton and solitary electron, was particularly responsive to gravitational forces. Small clumps of hydrogen began to attract one another, gradually forming dense clouds under the pull of gravity. Helium, being slightly heavier and chemically inert, mixed with hydrogen and contributed to the mass and pressure within these early clouds. Over millions of years, these primordial clouds of hydrogen and helium grew denser and hotter, eventually igniting the first nuclear reactions that marked the birth of the first stars. In these stars, hydrogen fused into helium, releasing enormous amounts of energy in the process, a phenomenon we now know as stellar fusion. This process not only powered the stars but also began the slow, intricate process of creating heavier elements, setting the stage for the formation of planets, moons, and ultimately life itself. It is important to understand the sheer scale of this cosmic transformation. The universe, still only a few million years old at this point, was gradually evolving from a featureless, glowing plasma into the first luminous objects. Hydrogen and helium, though individually simple, combined in vast quantities to create enormous clouds stretching for millions of light years across space. Within these clouds, gravity sculpted filaments, knots, and dense cores, like a sculptor shaping a block of marble. In these dense cores, the first stars ignited, and with their nuclear furnaces they would continue the work of element creation. The simplicity of hydrogen and helium was the necessary starting point. Without them, the universe would have remained dark and empty, devoid of the chemical diversity that allows galaxies, planets, and life to exist. The formation of hydrogen and helium also left an indelible mark on the observable universe. When the universe cooled further, roughly 300,000 years after the Big Bang, electrons combined with the nuclei of hydrogen and helium to form neutral atoms in a process known as recombination. This allowed photons, the particles of light, to travel freely through space for the first time, creating a glowing bath of radiation that we now observe as the cosmic microwave background. The composition of hydrogen and helium in this early universe directly influenced the density, temperature, and fluctuations observed in this background radiation. By studying these patterns, scientists can trace the precise proportions of hydrogen and helium, revealing clues about the first few minutes of cosmic history and the processes that governed the birth of matter. The legacy of hydrogen and helium extends even further. These elements became the primary fuel for star formation across the cosmos. In regions of dense hydrogen and helium clouds, gravitational collapse triggered the birth of stars. Stars of different masses formed, some burning for only millions of years, others for billions, synthesizing heavier elements in their cores. When massive stars ended their lives in spectacular explosions known as supernova, they spread these newly created elements into space, seeding future generations of stars and planets with the chemical diversity necessary for complex structures, including life. The universe, in essence, built itself from these two simple elements. Hydrogen provided the raw material for the ignition of stars, while helium acted as a stabilizing partner, allowing nuclear reactions to proceed efficiently. Together, they were the original architects of the cosmos. Even in the most distant galaxies we observe today, hydrogen and helium remain dominant. They continue to flow through the interstellar medium, feeding new star formation and regulating the chemical evolution of galaxies. The relative abundance of these elements is a testament to their origin in the Big Bang, a reminder that the universe has been governed by fundamental physical laws from the very beginning. Modern astrophysics confirms this through observations of distant quasars and ancient gas clouds, showing that the ratio of hydrogen to helium has remained remarkably consistent across billions of years. This consistency reinforces our understanding of the early universe and validates the predictions of Big Bang nucleosynthesis. The story of hydrogen and helium also underscores a deeper truth about the universe, that complexity arises from simplicity. From the smallest, most fundamental elements, the cosmos has evolved structures of breathtaking intricacy. Galaxies with billions of stars, planetary systems with diverse worlds, and even the conditions necessary for life on Earth all trace their origins back to these two elements. The universe, in its infancy, may have been simple and uniform, but the interactions of hydrogen and helium, governed by gravity and nuclear physics, set in motion a chain of events that would produce the astonishing variety we see today. From a handful of protons and neutrons in the first minutes after the Big Bang, the universe embarked on a journey that led to swirling galaxies, blazing stars, and eventually conscious beings capable of pondering their own origins. The immense abundance of hydrogen and helium also tells us about the limitations of what could form in the early universe. Elements heavier than helium, like carbon, oxygen, and iron, could not form until stars began to fuse hydrogen into helium and then into heavier nuclei. This means that the universe had to spend millions of years in a phase dominated by just these two elements before the first stars could produce more complex chemistry. In this way, hydrogen and helium acted as the primordial foundation upon which the entire chemical complexity of the universe would be built. They were both the starting material and the scaffolding for all subsequent cosmic evolution. In reflecting on the formation of hydrogen and helium, one cannot help but be awed by the elegance and inevitability of the process. These elements formed naturally under the conditions present in the first few minutes of the universe, a product of fundamental forces and simple physical laws. Their formation was neither chaotic nor random. It followed precise rules dictated by nuclear physics and the conditions of the expanding universe. The universe, in these first moments, demonstrated a remarkable order, producing the ingredients for all future cosmic structures with astonishing efficiency. Hydrogen and helium in their simplicity carried within them the potential for everything to come. They were not just elements, they were the blueprint for the cosmos. Over the course of billions of years, the humble beginnings of hydrogen and helium gave rise to galaxies, stars, and planets, eventually creating the environments necessary for life to emerge. Hydrogen would fuel stars for billions of years, while helium would stabilize their cores and contribute to the formation of heavier elements. Without the creation of these two elements in the first few minutes of cosmic time, the universe would have remained a dark, featureless expanse. Instead, it became a vibrant, evolving tapestry of matter and energy, driven by the simple, elegant physics that created hydrogen and helium in the first place. If we take a moment to look closely, we realize that much of what forms the magnificent structures we observe, planets, stars, moons, and even life itself, originates from something incredibly humble: clouds of dust and gas floating silently in the emptiness of space. These clouds, known in scientific terms as interstellar matter, may seem insignificant at first glance, mere wisps of particles scattered across unimaginable distances, but they are in truth the fundamental ingredients from which everything in the cosmos is made. Without them, planets like our Earth, the Sun, and indeed every star in the night sky would simply not exist. Interstellar matter is composed primarily of hydrogen and helium, the lightest and most abundant elements in the universe, alongside trace amounts of heavier elements such as carbon, oxygen, nitrogen, silicon, and iron. These heavier elements were not created during the Big Bang itself, but were forged later inside the hearts of stars through a process known as stellar nucleosynthesis. Over billions of years, stars lived and died, scattering their enriched material into the surrounding space through stellar winds, supernova explosions, and planetary nebulae. These dramatic cosmic events seeded the interstellar medium with the raw materials that would eventually clump together to form new generations of stars, planets, and ultimately the environments that could support life. Imagine a region in space filled with a tenuous, almost invisible mixture of gas and dust. While it may seem calm and static, this environment is far from lifeless. Tiny particles, each smaller than the width of a human hair, drift slowly through the void, colliding occasionally with one another. The gases in these clouds are extremely cold, sometimes just a few degrees above absolute zero, which is minus 273 degrees Celsius. In these conditions, gravity, though weak on a human scale, plays a crucial role. It gently pulls particles together, forming ever denser clumps. Over time, these clumps grow, their own gravitational pull increasing as more material gathers. This slow but persistent gathering is the first step toward the birth of stars and planets. Among the most fascinating and important types of interstellar matter are what scientists call molecular clouds, sometimes poetically referred to as stellar nurseries. These clouds are rich in molecules, primarily molecular hydrogen, and often contain a significant amount of cosmic dust. Dust grains, which consist of tiny bits of silicate minerals, carbon compounds, and ice, serve as surfaces upon which more complex chemical reactions can occur. In these dark, dense regions, ultraviolet light from distant stars is largely blocked, allowing the dust and gas to cool to extremely low temperatures. This cooling is essential because it slows the motion of particles, giving gravity the opportunity to overcome thermal pressure and pull matter together. It is within these dark, cold clouds that the universe begins the intricate process of building planets. As these clouds condense, small pockets of higher density called clumps form. Within these clumps, gravity continues to work, drawing in gas and dust, causing the material to spin and flatten into what astronomers call a protoplanetary disk. This disk can extend for hundreds of billions of kilometers, surrounding a newborn star at its center. Within the disk, dust grains collide and stick together, gradually forming larger and larger aggregates. Over thousands and even millions of years, these aggregates can grow from mere micrometers in size to pebbles, then boulders, and eventually to planetesimals, which are objects that can be tens or even hundreds of kilometers across. These planetesimals are the true building blocks of planets, the seeds from which entire worlds will grow. One of the most fascinating aspects of this process is how ordinary, almost invisible dust grains can give rise to planets that are massive enough to sustain atmospheres, oceans, and even life. When planetesimals collide, they can either merge, forming larger bodies, or shatter into smaller fragments, contributing more material to the surrounding disk. Gravity continues to dominate this chaotic environment, gradually assembling protoplanets. Over tens of millions of years, these protoplanets clear their orbital paths, gather more material, and may undergo further collisions that shape their final structure. Some become rocky planets, like Earth and Mars, while others, capturing vast envelopes of gas, become giant planets like Jupiter and Saturn. This slow but relentless sculpting of matter from dust and gas into planets is one of the most remarkable transformations in the universe. It is also important to understand that cosmic dust is far from uniform. Some particles are rich in silicates, others in carbon, and still others in metals like iron and nickel. This diversity in composition contributes directly to the variety of planets that form. Rocky planets tend to incorporate a higher proportion of silicates and metals, whereas gas giants accumulate massive envelopes of hydrogen and helium, reflecting the composition of the original cloud. Even within a single planetary system, differences in temperature, pressure, and composition across the disk lead to a wide range of planetary types, from icy moons to lava-covered worlds. The initial ingredients, the dust and gas, determine the ultimate diversity of planets, moons, and other celestial bodies. Beyond the formation of planets, interstellar dust also plays a crucial role in regulating the chemistry of the galaxy. Dust grains can shield molecules from destructive ultraviolet light, allowing complex organic molecules to form in the cold recesses of space. These molecules include water, methane, ammonia, and even amino acids, which are the building blocks of life. Some scientists propose that this cosmic chemistry may have been essential for the emergence of life on Earth, as meteoroids and comets, formed from ancient dust, delivered these organic molecules to our planet billions of years ago. In this sense, dust and gas are not only the foundation of planets, but also potential precursors to life itself, linking the formation of stars and planets to the grand story of life in the universe. Observations of distant star-forming regions in our own galaxy, the Milky Way, and in other galaxies provide stunning visual evidence of this process. Images from telescopes like the Hubble Space Telescope and more recently the James Webb Space Telescope reveal dark lanes of dust threading through glowing clouds of gas. These images show regions where stars are being born, their intense radiation creating bubbles and shock fronts that can trigger further star formation. Within these regions, disks of dust and gas can be seen surrounding young stars, the very sites where planets are likely forming even now, Each of these clouds is a dynamic, evolving laboratory, demonstrating the universality of the processes that lead from simple dust and gas to complex planetary systems. The story of cosmic dust and gas also extends back to the very beginnings of the universe. After the Big Bang, which occurred approximately 13,800,000,000 years ago, the universe was filled mostly with hydrogen and helium gas, with only trace amounts of lithium and beryllium. Heavier elements did not exist yet. It was through generations of stars forming, living and dying that the heavier elements essential for planets were created. Each supernova explosion scattered these elements across space, enriching the interstellar medium and making it possible for future stars and planetary systems to form with a richer variety of materials. In this way, the dust and gas clouds we observe today are not primordial in the strictest sense. They carry the legacy of countless stars that came before, making every planet, including Earth, a product of cosmic recycling on an unimaginable scale. Even within our own solar system, we see the fingerprints of cosmic dust everywhere. Comets, asteroids, and meteorites all contain material that predates the formation of the Sun and planets. These ancient relics preserve the composition of the primordial dust and gas from which our planetary system formed over 4,500,000,000 years ago. By studying these objects, scientists can gain insights into the very conditions that existed in the early solar nebula, learning not only about the materials themselves but also about the processes that assembled them into planets. Meteorites, for example, often contain tiny spherical grains called chondrules, which were formed from molten droplets in the early solar system. These chondrules, along with the dust that surrounds them, tell the story of the violent and chaotic environment in which our planets were born. In addition to building planets, cosmic dust has profound effects on the light that travels through space. Dust scatters and absorbs starlight, creating phenomena such as the reddening of distant stars or the dark silhouettes seen against glowing nebulae. Without dust, our universe would look very different. The diffuse glow of galaxies, the intricate filaments of nebulae, and the colours that captivate astronomers and the public alike would be diminished. In a sense, cosmic dust not only forms planets, but also shapes the very appearance of the universe, turning invisible matter into a canvas upon which light paints the history of stars and galaxies. It is astonishing to reflect that something as seemingly insignificant as tiny particles of dust and gas, floating silently in the darkness of space, holds the key to the formation of entire worlds. These particles, governed by gravity and guided by chemistry, can come together over millions and billions of years to create planets capable of oceans, atmospheres, and life itself. Each planet, moon, and asteroid in our solar system is a testament to the power of these humble building blocks. Without them, there would be no Earth, no Mars, no Jupiter, and no distant exoplanets orbiting stars hundreds or thousands of light years away. Every piece of matter in our solar system is a product of cosmic dust and gas, shaped over eons by the delicate interplay of forces that govern the universe. It begins in a quiet, dark and cold region of the galaxy where thick clouds of gas and dust had drifted for millions of years. These clouds, known as molecular clouds, were the raw nurseries of stars. They contained the simplest ingredients of the universe, hydrogen and helium, along with tiny traces of heavier elements such as carbon, oxygen, nitrogen, and iron, which had been created in earlier generations of stars that lived and died long before our sun was born. Within these enormous clouds, gravity was always at work, slowly tugging at the particles of matter, gathering them together, and preparing for a great transformation. The event that would change everything was the collapse of part of one of these clouds, a collapse that triggered the birth of the sun. To understand the gravity of this moment, we must picture the conditions inside these molecular clouds. They were not uniform or smooth, but lumpy, filled with denser knots of material surrounded by more diffuse gas. Some of these knots were much colder and denser than the space around them, and it was inside such knots that the seeds of stars were hidden. For countless years, these knots remained quiet, balanced by a delicate struggle between the inward pull of gravity and the outward push of gas pressure. Gravity wanted to pull everything inward to bring the particles closer together. Gas pressure, on the other hand, resisted this inward pull, trying to keep the material spread apart. As long as these two forces were in balance, The knot of gas and dust remained stable, a dark and quiet place with no light of its own. But balance in the universe is a fragile thing. Something eventually disturbed it. Perhaps it was the shockwave of a nearby supernova, the violent explosion of a massive star that had come to the end of its life. Such an explosion sends ripples of energy and waves of compressed gas rushing across space, colliding with nearby clouds. Perhaps it was the slow merging of smaller clumps of gas, or the steady tug of gravity as the knot became heavier with time. Whatever the exact cause, one particular region of a molecular cloud about 4.5 billion years ago could no longer resist the pull of gravity. The struggle between pressure and gravity was lost, and gravity won. The collapse began. When gravity takes control, the process is both slow and unstoppable. At first, the collapse was gentle, with gas and dust particles drifting closer together. But as they came together, their combined gravity grew stronger, pulling in even more material. The denser the knot became, the faster it pulled matter toward itself. This created a runaway effect, a chain reaction in which the collapse fed upon itself. Each bit of matter added to the knot increased its gravitational pull, which in turn pulled in more matter. It was as if the cloud had suddenly awakened after millions of years of slumber, now rushing to form something entirely new. As the collapse continued, the temperature inside the knot began to rise. When particles fall inward under gravity, their movement speeds up, and their collisions grow more frequent and energetic. The kinetic energy of these particles, converted into heat, began to warm the center of the collapsing cloud. What was once a frigid and dark knot of gas, colder than even the coldest night on Earth, slowly grew warmer. A new kind of object began to emerge at the very center. A protostar, the unborn form of the Sun. Surrounded by a vast, swirling envelope of gas and dust, this protostar was the heart of the collapse, glowing faintly with the heat of compression. The protostar did not form in isolation. As the material spiraled inward, it did not fall directly into the center, but instead flattened into a disk around the forming Sun. This was due to the conservation of angular momentum, a fundamental principle of physics. Any slight rotation in the original cloud knot was amplified as the collapse occurred, much like a figure skater spinning faster as they pulled their arms inward. The result was a spinning disk of material around the newborn Sun, a disk that held the seeds of planets, moons, asteroids, and comets. But for now, the focus remained on the central growing protostar, which continued to gather mass from the surrounding cloud. The collapse itself was not smooth or even. It was turbulent, chaotic, and violent in places. Magnetic fields threaded through the cloud, twisting and snapping as the material shifted. Shock waves and instabilities rippled through the gas, sometimes fragmenting the cloud into smaller clumps that could form other stars nearby. Indeed, our Sun was likely not born alone, but as part of a cluster of stars, siblings born from the same collapsing cloud. Some of those stars may still exist today, scattered across the Milky Way galaxy, though it is nearly impossible to identify them after billions of years of drift and separation. The collapse of the cloud, therefore, was not merely the birth of one star, but the creation of an entire family of stars, each with its own system of planets or debris. As more material poured into the center, the protostar grew larger and hotter. The surrounding disk fed it like a river feeding a lake, and streams of gas funneled inward. At the same time, jets of material were launched outward along the poles of the forming star, powered by magnetic interactions. These jets cleared away much of the surrounding gas, shaping the young solar system and announcing to the universe that a new star was in the making. Still, the process of collapse was far from over. For millions of years, the protostar continued to gather material, growing heavier and hotter, its interior pressures climbing to astonishing levels. The key turning point in the collapse came when the pressure and temperature at the center of the protostar reached the point where nuclear fusion could begin. This moment was the true birth of the Sun. Hydrogen atoms, the simplest and most abundant atoms in the universe, were squeezed together so tightly that they fused into helium, releasing vast amounts of energy in the process. The energy from fusion pushed outward with incredible force, creating a new balance. Gravity still pulled inward, trying to collapse the star further, but now the outward pressure from fusion energy countered it perfectly. The collapse had finally ended. a star had been born. But let us not rush too quickly to this grand conclusion, for the details of the collapse are as fascinating as its outcome. The process took millions of years, a span of time so vast that human history seems like a blink in comparison. From the first moment of imbalance when gravity began to win to the final ignition of fusion, the cloud transformed through countless stages. The central protostar brightened slowly, first glowing only in the infrared spectrum, invisible to human eyes but detectable to sensitive instruments. The disk around it became the workshop of planets, where dust grains stuck together, forming pebbles, then rocks, then ever larger bodies. The collapse of the molecular cloud, therefore, not only created the Sun, but also set in motion the processes that would create the Earth and every other planet of the solar system. The collapse also carried with it the history of the universe. The elements within the cloud were not random. The hydrogen and helium had been created in the Big Bang billions of years earlier. The heavier elements such as carbon, oxygen, silicon and iron were the ashes of ancient stars, thrown into space by supernova explosions or the winds of dying giants. When the cloud collapsed, it gathered all these elements together into a new star and its surrounding worlds. In a sense, the collapse was not the beginning of a story but a continuation, a new chapter in the eternal cycle of cosmic creation and destruction. Stars lived, died, and seeded the clouds, and from those clouds, new stars were born. Our Sun was one such star, a child of this cycle, and its birth was written in the collapse of a cold, dark cloud. Even as the Sun stabilized and fusion began, traces of its turbulent birth remained. The solar system retained its flattened disk shape, with planets orbiting along the same general plane, a reflection of the rotating disk of material from the collapse. The composition of the planets reflected the materials present in the cloud. Rocky planets like Earth, Mars and Venus formed closer to the Sun, where only metals and silicates could survive the heat. Gas giants like Jupiter and Saturn formed farther out, where lighter elements such as hydrogen and helium could gather. Comets and icy bodies formed in the outer reaches, preserving the most pristine samples of the original molecular cloud. All of these worlds, in their variety and abundance, owe their existence to the collapse that created the Sun. If we look deeper, the collapse of the molecular cloud is a lesson in the power of gravity. It shows how a seemingly empty and quiet part of space can suddenly awaken with activity, drawing together material to create light and warmth where there was only cold and darkness before. It shows how balance in the universe is never permanent, how even the most stable cloud may someday collapse into something new. And it shows how the raw and simple ingredients of the universe, hydrogen, helium, and dust, can be shaped into something as magnificent as the Sun, a star that has burned for billions of years and will continue to burn for billions more. Over the immense stretch of time, the collapse that formed the Sun has been repeated countless times throughout the galaxy. Everywhere that molecular clouds exist, stars are born in the same way. Some are larger, some smaller, some live long lives, and some die young. But the process is universal. Clouds collapse, stars ignite, and worlds are formed. Our Sun is but one star among hundreds of billions in the Milky Way, and yet its collapse was special to us, for it gave rise to our home and our lives. And so the tale of the Sun's beginning is the tale of a cloud surrendering to gravity. It is the tale of balance lost and regained in a new form. It is the tale of fire born from coldness, of light born from darkness. 4.5 billion years ago, in a quiet corner of the galaxy, a molecular cloud collapsed, and in that collapse, the Sun was born. From that moment, the stage was set for the formation of the solar system, the rise of Earth, and eventually the emergence of life itself. The collapse was not merely an astronomical event, it was the opening act in the story of existence. Billions of years ago, there was no Sun. There was only a vast, cold and dark stretch of space, filled with clouds of gas and dust drifting silently. Somewhere within that immense emptiness, the seeds of our Sun began to stir. To understand how this great star came to life, we must travel back in time, far beyond the age of humans, far beyond the age of the Earth itself, to an era when our solar system was only a thought written into the laws of nature, waiting to unfold. The beginning of this story lies about 4.5 billion years ago, when a massive molecular cloud, rich with hydrogen gas, helium, and tiny specks of dust, floated in a distant corner of the Milky Way galaxy. This cloud had no special purpose. It was just one among countless others spread across the galaxy, left behind by the deaths of older stars that had exploded in magnificent supernova blasts. These explosions had scattered the elements of those stars into space, mixing them into vast clouds. The cloud that would eventually give birth to the Sun was not unique at first, but something happened that would transform it into the cradle of our solar system. Perhaps it was the shockwave of a nearby exploding star that shook this cloud, or maybe it was the natural movement of gas under the gentle pull of gravity. Whatever the trigger, the calm balance of this cloud was disturbed, and gravity began to take over. Gravity is one of the most patient and powerful forces in the universe. It pulls every speck of matter toward every other speck, and when a cloud is massive enough, gravity can cause it to collapse inward. In this case, that is exactly what happened. The gas and dust began to clump together, drawing tighter and tighter toward the center of the cloud. What had been a cold, quiet region of space became a place of swirling movement and increasing heat. As the collapse continued, more and more material collected at the heart of this growing knot. Every bit of matter that joined the gathering center released energy, which raised the temperature. Slowly but relentlessly, a dense and hot ball of matter formed. This was not yet the Sun we know, but the earliest stage of its life, called a protostar. A protostar is like a star in its infancy, not yet fully ignited, but glowing faintly with the heat of its own growing weight. The pressure inside it rose as more gas and dust piled on, and this pressure struggled to resist the inward pull of gravity. It was a delicate battle between two forces, the crushing grip of gravity and the expanding push of heat and pressure from within. At this point in its story, the protostar was wrapped in a cocoon of gas and dust. If someone could have looked at it from the outside, it would not have looked like the bright shining sun we see today. Instead, it would have appeared as a glowing ball hidden within a swirling chaotic cloud, with streams of matter spiraling into it. The heat at its core was rising to millions of degrees, and deep inside something remarkable was preparing to happen. To understand why this stage was so important, we must remember that stars are not just balls of fire. They shine because of a process called nuclear fusion, in which atoms of hydrogen, the simplest and most abundant element in the universe, are forced together under intense heat and pressure to form helium. When this happens, a huge amount of energy is released, much greater than any fire or chemical reaction known on Earth. This energy is what makes stars shine for billions of years. For our protostar, the moment when nuclear fusion would begin was still ahead, but all the conditions were slowly coming together. The gravitational collapse was not a smooth process. The surrounding cloud of gas and dust spun as it fell inward, forming a flattened disk around the growing protostar. This disk was important because it contained the leftover material that would one day form the planets, moons, asteroids and comets of our solar system. But at the center of the disk, the protostar continued to grow heavier and hotter. It was still gathering matter, pulling in everything it could from its surroundings, becoming brighter and denser. After millions of years of steady collapse, the conditions at the core of the protostar reached a turning point. Temperatures soared to around 10 million degrees Celsius, and the density became so high that hydrogen atoms could no longer remain separate. They began to fuse into helium, and with this fusion, the Sun was truly born. The protostar had now crossed into the stage of a main sequence star, and it lit up with the brilliance that would continue for billions of years. The birth of the Sun was a moment of cosmic balance. Gravity had pulled matter inward for so long, but now the energy of fusion pushed outward with equal force. The star stopped collapsing and stabilized, shining steadily in the darkness of space. It was the moment when our solar system gained its beating heart. The swirling disk of material around it would eventually coalesce into planets, but without the Sun's warmth and energy, those planets would have been lifeless rocks and ice. The transformation from a cloud of gas and dust into a blazing star was not only a physical event, but also the start of countless future stories. Around the newborn Sun, the disk continued to spin and clump together, forming the early building blocks of the planets. Small grains stuck together to make pebbles. Pebbles grew into rocks, and rocks into giant planetesimals that would crash and merge to form the worlds we know today. The Sun, at the centre, continued to shine brighter, stabilising the system and holding it together with its gravity. What makes the Sun's birth even more wondrous is the thought that this process has happened many times across the galaxy and continues even now. Stars are constantly being born in giant nurseries of gas and dust, much like the one that gave us our Sun. When we look at places like the Orion Nebula or the Eagle Nebula, we are seeing new stars being born in clouds very much like the one from which our solar system emerged. Each star has the potential to give rise to planets, and some of those planets may even host life. The Sun's birth, then, is not just our story, but a chapter in the greater story of the universe itself. Billions of years after its formation, the Sun continues to shine, sustaining Earth and shaping every aspect of life. But it is humbling to think of its beginnings, hidden in a cold, dark cloud, sparked into existence by the slow but unstoppable force of gravity. From that simple beginning, a chain of events unfolded that led to Earth, to oceans, to forests, to human beings who could one day look up at the sky and wonder about their origins. The Sun's journey from a protostar to the star we see today was not quick. It took millions of years of patient gathering, collapsing and heating before nuclear fusion could begin. During that time, the balance between gravity and pressure determined whether the star would survive or fail. If the protostar had been smaller, it might never have reached the temperatures needed for fusion, and it would have become a failed star known as a brown dwarf. But the mass of our protostar was great enough, and gravity strong enough, to ignite the fire of fusion. This is why the Sun is not just any star. It is the right kind of star, with the right amount of mass to provide the long-lasting energy that life requires. The Sun has now been burning for about 4.5 billion years, and it has enough fuel to continue shining for at least another 5 billion years. In that time, it will change, grow hotter, and eventually expand into a red giant. But that is a story for another day. For now, the important truth is that the Sun, our star, was born in the heart of a collapsing molecular cloud, rose to life as a protostar, and ignited into brilliance through the power of nuclear fusion. It is easy to take the Sun for granted, to think of it as just the bright light that rises every morning. But when we trace its story back to its origins, we see that its birth was the result of countless cosmic events stretching across billions of years. The death of older stars provided the material, gravity shaped it into a dense core, and fusion lit the fire that still burns today. The Sun's story is a reminder that everything around us, our planet, our bodies, our very thoughts, comes from the same cosmic chain of creation. When we step outside and feel the warmth of sunlight on our skin, we are feeling the ancient energy of nuclear fusion that began billions of years ago when the Sun was born. That warmth travelled through space, across millions of kilometres, to reach us, carrying with it the memory of the Sun's birth. It is as if every ray of sunlight is a messenger from the dawn of our solar system, telling us the story of where we came from. This story, though vast and filled with numbers too great to fully grasp, is also deeply personal. The Sun's birth made possible the world we live in. Without it, there would be no oceans, no forests, no animals, and no people to wonder about their place in the universe. Its formation was not just a cosmic event, but the foundation of everything that followed. From a cold and silent cloud, gravity sculpted a star, and from that star came a system of planets, one of which would one day give rise to life and thought. That is the true wonder of the Sun's birth. It was the beginning not just of a star, but of the long path that led to us. The protoplanetary disk, that great swirling mix of gas and dust that once surrounded the young Sun, is one of the most important chapters in the long history of our solar system. Without this disk, there would be no Earth beneath our feet, no moon above our heads, no planets, no asteroids, and no comets. Everything we see when we look into the night sky and call part of the solar system had its beginnings in that huge spinning cloud of cosmic material. To truly understand how our world came to be, we must step back billions of years into a time when the Sun was still very young, and the space around it was alive with motion, chaos, and creation. The Sun, after it first formed as a glowing ball of hot plasma, did not stand alone in empty space. It was born inside a giant cloud of gas and dust that collapsed under its own gravity. Much of the material rushed toward the centre to feed the growing star, but not all of it fell inward. Instead, the laws of physics caused much of that gas and dust to flatten into a wide, spinning disk around the new sun. This was the Protoplanetary disk, the birthplace of the planets. It was like a great cosmic workshop where raw materials were slowly transformed into the worlds we know today. The disk itself stretched for an enormous distance. It was not something small and compact, but a structure that extended far beyond where the outermost planets now circle. In the earlier stages, it was dense with dust grains, icy particles, and hydrogen and helium gas, the two simplest and most common elements in the universe. At first glance, this mixture may have seemed like nothing more than a cloudy fog, but within it lay the potential for everything. The rocks, the seas, the mountains, the clouds, and even life itself. The Earth, Jupiter, Saturn, and every other planet began as tiny particles within this spinning soup of cosmic material. The reason the disk formed a flat shape instead of remaining a simple cloud lies in the way motion works. When the great molecular cloud that gave birth to the sun collapsed, it began to spin faster and faster, just as an ice skater spins faster when pulling in their arms. This rapid spin caused the material to flatten into a disk, much like dough being pressed flat by a rolling pin. At the centre blazed the new sun, while around it swirled a glowing halo of gas and dust that stretched in all directions. The disk was not uniform. It had regions of higher and lower density, hotter and cooler zones, and areas where different elements could gather and interact. These variations played a critical role in shaping the planets that would form later. Closer to the sun, the disk was extremely hot, so only metals and rocky materials could survive there. Lighter substances like water, methane, and ammonia could not remain solid in that heat. They evaporated and were driven outward. Farther away, beyond a certain boundary known as the frost line, temperatures dropped low enough for ices to form and remain stable. This simple difference between the inner and outer regions of the disk explains why the inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds, while the outer planets, Jupiter, Saturn, Uranus, and Neptune, are made largely of gas and ice. It all began with the way the protoplanetary disk divided its materials. Inside the disk, dust grains constantly collided with one another. At first, these collisions were gentle, and the grains stuck together through tiny electric forces, forming larger clumps. Over time, clumps grew into pebbles, pebbles into boulders, and boulders into mountain-sized bodies known as planetesimals. These planetesimals were the true seeds of planets. Gravity soon began to play its role, pulling more and more material together until these bodies became massive enough to dominate their regions of the disk. The process was slow and chaotic, filled with violent impacts and near misses, but it was through this turmoil that the planets were born. The protoplanetary disk was not quiet or still. It was a restless place, with streams of gas flowing inward, giant shock waves rippling through the material, and the newborn sun blasting it with intense radiation. The young star emitted powerful solar winds and bursts of ultraviolet light, which pushed against the gas in the disk. Over millions of years, this radiation began to sweep away the remaining lighter gases, thinning the disk and leaving behind the solids that had already formed into larger bodies. This process, called disk dispersal, sets a time limit for planet formation. If a planet did not gather enough material before the gas was blown away, it would remain small and rocky. That is why the outer giants, like Jupiter and Saturn, had to grow quickly. They gathered massive envelopes of gas before the sun's winds stripped the disk clean. Jupiter, in fact, may have been the first planet to fully form. Its immense gravity allowed it to pull in enormous amounts of hydrogen and helium, while the disk was still thick with gas. Its birth may have shaped the fate of the rest of the solar system, stirring up the disk and influencing the growth of other planets. Saturn, Uranus, and Neptune followed, building their own massive atmospheres from the rich supply of gas that was available in the cooler outer regions. Closer in, where gas had already been lost or could not survive, the rocky planets took shape from the solid debris that remained. The creation of the asteroid belt between Mars and Jupiter can also be traced back to the protoplanetary disk. In that region, The powerful gravity of Jupiter stirred the material so violently that no single planet could form. Instead, countless smaller bodies remained, creating a belt of rocky fragments that circles the Sun to this day. Similarly, at the far edges of the disk, icy planetesimals that never grew into full planets became comets, locked in distant reservoirs like the Kuiper Belt and the Oort cloud. But the story of the protoplanetary disk is not only about physical structures, it is also about chemistry. The disk was a kind of chemical laboratory where simple elements combined into more complex molecules. Within the swirling dust, carbon-rich compounds, water ice, and organic molecules began to form. These molecules stuck to dust grains, were carried by icy comets, and eventually found their way to young planets. In this way, the disk planted the seeds of life itself. The oceans of Earth and even the molecules in our own bodies can trace their origins back to the chemistry of that ancient disk. Over the course of tens of millions of years, the once thick disk gradually thinned out. The sun's winds cleared the gas, the forming planets swept up much of the dust, and what remained either fell into the sun or was ejected into deep space. The disk that had once glowed brightly in the light of the young sun eventually disappeared. What was left behind was a solar system filled with newly born planets, moons, asteroids, and comets, each carrying the signature of the region of the disk where it had formed. Even though our own protoplanetary disk vanished billions of years ago, astronomers today can still study similar disks around young stars in the galaxy. With powerful telescopes, they can see glowing rings of dust and gas circling stars that are only a few million years old. These disks show striking patterns, sometimes with gaps where planets may already be forming. Each one is a living picture of what our solar system must have looked like in its youth. By studying them, scientists can piece together the details of our own origins. When we think about the protoplanetary disk, it is easy to see it as just a scientific concept, but it is more than that. It is the womb from which the Earth itself was born. Every rock, every drop of water, every breath of air we take is connected to that swirling cloud of dust and gas. Without it, there would be no us. It is humbling to realize that something as grand and chaotic as a cosmic disk gave rise to the delicate balance of life. The disk also teaches us something about the fragile balance of chance and order in the universe. The planets did not emerge from it in a neat, predictable sequence. They were shaped by random collisions, by sudden changes, by the push and pull of gravity. If events had gone differently, if a planetesimal had struck Earth too hard, or if Jupiter had formed closer to the Sun, the solar system might look nothing like it does today. Perhaps there would be no Earth at all, or no stable place for life to arise. Our existence depends on the long chain of events that unfolded within that swirling disk. Even after all these billions of years, the traces of the protoplanetary disk can still be felt. Comets that sweep through the inner solar system carry with them the ancient ices that condensed in its outer reaches. Meteorites that fall to Earth contain grains of dust that were once part of the original cloud. In this way, pieces of the disk still arrive at our planet, tiny messengers from the dawn of time. The protoplanetary disk is not just the beginning of planets, but the beginning of stories. Every world has its tale, written in the dust and gas of that ancient disk. The craters on the Moon, the rings of Saturn, the storms of Jupiter, and even life on Earth are all chapters in a story that began when the young sun was surrounded by a glowing halo of material. To study the disk is to read the first pages of that story, to see how the raw ingredients of a galaxy were gathered and reshaped into the worlds we know. When we look up at the night sky and see distant stars, many of them are young suns with their own disks. Around some of those disks, planets are forming at this very moment. Somewhere in that spinning dust, a new Earth may be taking shape. It is a reminder that our story is not unique, that the same process which gave us a home is happening again and again across the universe. The protoplanetary disk of our sun was just one among countless others, yet to us it was the most important of all, for it gave us life, memory, and the chance to wonder about the cosmos. When we try to imagine the early beginning of our solar system, it is tempting to picture great worlds, giant planets, and blazing suns forming in an instant, as though someone switched on the lights of the cosmos. But the truth is far slower, more patient, and in many ways even more magical. The The process that gave birth to the planets we know today did not begin with large bodies at all. Instead, it began with dust. Dust so fine that each grain was no larger than the width of a human hair, floating silently in the wide disk of gas and particles that circled the young sun. From this humble dust, the mighty Earth and the giant Jupiter would one day rise, and the way this happened is through a process called accretion. Accretion is the story of how little things come together to make big things. At first, there were only tiny grains of minerals, frozen gases, and microscopic bits of metal drifting around. These grains collided softly with one another. Most collisions were so weak that the particles just bounced off each other. But sometimes, when conditions were right, the particles stuck together, forming clumps. It was as if the dust had a quiet stickiness that allowed it to gather into something bigger. Over millions of years, these clumps grew larger and heavier, slowly becoming what scientists call planetesimals, the small building blocks of planets. The scene billions of years ago was not calm. The swirling disk of gas and dust around the young sun was constantly in motion. Every particle moved under the pull of gravity, dragged by currents of gas and jostled by other particles nearby. Imagine being inside a thick fog where every speck of mist is colliding with another, pushed and pulled in different directions. In that endless dance, some of the dust stuck together and refused to let go. This sticking happened because of simple forces like static electricity, and later because of gravity itself. In the beginning, static electricity worked like the charge you feel when you rub a balloon against your hair. Tiny dust grains developed small electric charges, and when two grains with opposite charges touched, they clung together. One grain plus one grain became two, then three, then a small cluster. This might seem insignificant, but in a place where there were trillions upon trillions of particles, the chances of such sticking events happening were enormous. Even though most collisions failed, enough succeeded to start a chain reaction of growth. These little clusters of dust were fragile. If struck too hard, they would shatter back into smaller pieces. But when conditions were gentle, they managed to survive and grow. Over thousands and millions of years, the clusters grew into pebbles, then into stones, and then into boulders. Imagine pebbles floating in space, bumping into one another, and combining to make rocks the size of houses. Step by step, the scale increased. At some point, gravity itself began to play a role. When an object became large enough, its own tiny gravity helped it attract more material. Instead of waiting for random collisions, it began pulling dust and smaller rocks toward itself. Growth became faster. The journey from dust to planetesimals was not simple or guaranteed. Many obstacles stood in the way. Some scientists even call it the meter-size barrier, because objects about the size of a meter face serious problems. At that scale, collisions often became destructive. Instead of merging, the rocks smashed into pieces. On top of that, gas flowing through the disk acted like a drag, slowing down the rocks and causing them to spiral into the young sun. In theory, many objects at this size should have been lost. But somehow, enough of them survived to continue growing. One possible solution to this mystery is that turbulence within the disk created special pockets where dust and rocks gathered in higher concentrations. These clumps acted like safe harbours, allowing rocks to grow past the dangerous stage. Another idea is that sticky organic molecules on the dust grains helped them cling more tightly. Over time, whatever the exact process, enough particles crossed the barrier and kept growing. Once they became large enough, kilometers across, they had strong gravity that held them together firmly. These bodies were no longer fragile clumps of dust. They were planetesimals, the true seeds of planets. Planetesimals were the first solid worlds of the solar system. They were far smaller than the planets we know today, but they were mighty compared to their humble beginnings as dust. Some were only a few kilometers wide, while others reached hundreds of kilometers across. These planetesimals collided with one another, sometimes merging, sometimes shattering. The larger ones survived and grew even larger, while smaller ones were often destroyed or absorbed. This chaotic process lasted for millions of years, shaping the early architecture of the solar system. The collisions between planetesimals were often violent. When two bodies of several kilometers across crashed into one another, the energy released could melt rock and metal. Sometimes, entire bodies were torn apart. At other times, the collisions produced molten droplets that cooled into new, round shapes. Meteorites that fall to Earth today sometimes carry evidence of these early fiery events, giving us a glimpse of the violence of planetesimal formation. Yet, despite the chaos, the overall trend was toward growth. The bigger a planetesimal became, the stronger its gravity was, and the more material it attracted. This runaway process is sometimes described as the rich get richer. Large bodies grew faster and faster, while smaller ones struggled to keep up. Within tens of millions of years, the largest planetesimals evolved into protoplanets, embryonic planets that would eventually form the Earth, Mars, and the other worlds we know. The story of accretion is also the story of chance. If we could replay the process, the results might look very different. Some planetesimals were flung out of the solar system entirely, becoming lonely wanderers in interstellar space. Others were pulled into the sun and destroyed. Still others collided at just the right angle to create moons or rings. Our own moon, for example, may have been born from a colossal collision between the young Earth and a Mars-sized planetesimal billions of years ago. Without such accidents, the solar system we see today might not exist. Even the gas giants like Jupiter and Saturn began with planetesimals. In their cases, the process went further. Once their solid cores reached a certain size, perhaps 10 times the mass of Earth, they were able to pull in vast envelopes of hydrogen and helium gas from the surrounding disk. This made them grow into the enormous planets we see today. Without accretion building their rocky and icy cores first, these giants would never have formed. To truly appreciate accretion, one must imagine the patience of time itself. Dust grains clumped together over thousands, millions, and even billions of years. Each step seemed small, but together they built worlds. The Earth we live on, the ground beneath our feet, the mountains, the oceans, all began as particles no bigger than dust floating in space. The same is true for every planet, every asteroid, every icy moon. All of them are products of accretion, the quiet but relentless process that transforms dust into worlds. This story is not unique to our solar system. Around distant stars, telescopes have spotted disks of gas and dust that glow in infrared light. In some of these disks, dark gaps appear, signs that young planets are already forming, sweeping up material through accretion. These distant systems show us that our solar system's story is part of a greater cosmic pattern. Everywhere in the universe, dust gathers, sticks, and grows into planets. The details may vary, but the principle remains the same. From the smallest beginnings, great worlds are born. What makes this story even more astonishing is that it all depends on simple forces. The same static cling that makes a balloon stick to a wall, the same gravity that pulls an apple to the ground, the same collisions that knock marbles together. These are the forces that shaped entire planets. The universe does not need sudden miracles. It only needs time and patience. Given enough time, the tiniest particles will gather into mountains, continents, and worlds. Accretion also holds the key to understanding the history locked inside meteorites. Some meteorites are pieces of ancient planetesimals that never grew into full planets. They are like time capsules from billions of years ago, carrying within them the textures of dust grains that once stuck together, the melted remnants of collisions, and even traces of the earliest chemistry of the solar system. By studying these rocks, scientists can look back into the very beginnings of accretion. The Earth itself still bears scars of its accretionary past. Its core, made of iron and nickel, likely formed when heavy metals sank to the centre of a growing planetesimal. Its crust and mantle grew from countless smaller collisions. Even water may have been delivered by icy planetesimals from the outer regions of the solar system. Every part of our world is a direct product of the long, slow gathering of dust into larger and larger bodies. If we think deeply about it, there is something poetic in the idea of accretion. It tells us that greatness begins with the smallest of things. A grain of dust, insignificant on its own, can be part of a chain that leads to mountains, oceans, and life. The story of planets is the story of dust refusing to stay alone, choosing instead to stick, to gather, and to become something greater. Even today, accretion continues in smaller ways. Rings around planets like Saturn are filled with icy particles colliding and sticking together, sometimes forming temporary moonlets. Asteroids in the belt between Mars and Jupiter still crash and fuse, shaping new fragments. On a much smaller scale, even raindrops in clouds form by a similar principle. tiny droplets gathering more and more material until they are heavy enough to fall. In this way, accretion is not only a cosmic process but also a familiar one that echoes in many corners of nature. But the truth is, they are the result of billions of years of change, of slow and steady growth. Every world we see is a monument to accretion, the patient sculptor of the universe. The next time you hold a handful of dust, imagine that given enough time, those grains could become a world. It is a thought both humbling and inspiring. How our solar system and its planets came to be is not only a tale of fire, dust, and gas, but also a long and patient journey of growth. At the heart of this story lies a fascinating stage, often called the formation of planetary embryos. This stage is one of the most important steps in turning small bits of rock and ice into something that looks like a planet. It is the chapter where the countless tiny building blocks of the early solar system, known as planetesimals, began to gather together, stick, and grow into larger bodies that could eventually become planets. To understand this process, we need to imagine a world long before Earth existed, long before any of the familiar planets took shape, when the Sun had only recently been born and the disk of gas and dust around it was alive with endless collisions, chaos, and slow but steady creation. At the beginning, everything started with the protoplanetary disk that surrounded the young Sun. This disk was made of swirling gas, ice, and dust left over from the Sun's birth. Within this disk, dust grains, smaller than the width of a human hair, drifted and stuck together. Over thousands and millions of years, these tiny grains clumped into larger pebbles and rocks, and these in turn formed planetesimals, which were like the seeds of future planets. A planetesimal was not yet a planet, not even close, but it was far larger than a dust grain. Some were just a few kilometers across, others tens or hundreds of kilometers. They were solid objects, with enough gravity to pull on each other and sometimes collide. Imagine billions upon billions of these planetesimals scattered through the swirling disk, like gravel spread across a gigantic cosmic construction site. But a universe filled with rocks does not make planets on its own. Something much more dramatic had to happen. This is where the formation of planetary embryos comes in. A planetary embryo is like a half-finished planet, larger than a planetesimal, yet smaller than a fully formed world. It is the middle stage of growth, and it is in this stage that the path from chaos to order really began. Embryos grew when planetesimals collided and stuck together. Every collision meant a chance for growth, though not every crash was successful. Some impacts shattered the objects into fragments, but many times the force of gravity made the pieces stay together after the collision, forming a bigger body. With every successful merger, the growing embryo gained more mass, and the larger it became, the stronger its gravity grew. This created a powerful cycle. Bigger objects could pull in smaller ones more easily, and this meant they grew even faster. This runaway growth is one of the most fascinating parts of the story. In the early disk, not every planetesimal was equal. Some by chance were a little larger than others, and that gave them a slight advantage. With slightly stronger gravity, they could draw in nearby smaller bodies more effectively. This advantage grew quickly, and soon those few lucky planetesimals ballooned into much larger objects. These were the first planetary embryos. In this way, a relatively small difference in size could mean the difference between staying small forever or becoming one of the true building blocks of a planet. The time it took for embryos to form was long by human standards, but very short in cosmic terms. Within just a few million years after the Sun's birth, many planetary embryos had already taken shape in the disk. Imagine an ocean of space filled with hundreds, maybe even thousands of these giant bodies, some as small as the Moon, and others nearly as big as Mars. They orbited the Sun in paths that often crossed one another, and their interactions were anything but calm. Collisions between them were fierce and violent. These impacts released enormous amounts of energy, enough to melt rock, create craters, and in some cases even strip away atmospheres or shatter embryos into pieces that would later reassemble. Far from being a quiet process, the growth of embryos was a dramatic dance of destruction and creation. The embryos continued to grow not only by eating planetesimals, but also by colliding with each other. When two embryos met, the result could be spectacular. Sometimes they merged into a larger embryo, while other times the crash was so intense that both bodies were left broken apart. Yet in the long run, these collisions drove the system forward, slowly reducing the number of bodies while increasing the size of the survivors. This process of fewer but larger bodies is what eventually paved the way for the planets we see today. One of the most extraordinary examples of this violent growth is believed to have shaped our own Earth. Scientists think that more than 4 billion years ago, when Earth was still an embryo itself, it collided with another large embryo, often called Theia. The impact was so enormous that it blasted material into space, and this material later gathered together to form the Moon. Without the stage of planetary embryos and their epic collisions, Earth would not have gained its satellite, which plays such an important role in shaping tides and stabilizing Earth's tilt. The embryos did not grow in the same way everywhere in the solar system. Close to the Sun, where it was hotter, the embryos were mostly made of rock and metal. In these regions, water and other ices could not survive the heat, so only solid rocky materials were available. This is why the inner planets, Mercury, Venus, Earth and Mars, are rocky worlds. Farther from the Sun, beyond what is called the frost line, temperatures were cold enough for ice to survive. Here the embryos could gather not just rock but also large amounts of ice. These icy embryos grew faster and larger, and they would eventually help form the cores of the giant planets like Jupiter and Saturn. In fact, it was the rapid growth of these icy embryos that allowed them to capture vast envelopes of gas from the disk, turning them into the giants we see today. In the outermost reaches of the solar system, embryos formed more slowly, because the material was spread out thinly and collisions were less frequent. Yet even there, some large bodies took shape, such as the ones that would eventually become Pluto and other dwarf planets in the Kuiper belt. These distant embryos tell us that the process of growth was universal, happening everywhere in the disk, though with different outcomes depending on location. The journey from planetesimals to embryos and then to planets is also a story of survival. Not every embryo made it to the end. Many were destroyed in collisions. Others were thrown out of the solar system entirely by the gravitational influence of larger neighbours like Jupiter. Some were left stranded in places like the asteroid belt, where growth was halted by the disruptive presence of Jupiter's gravity. In fact, the asteroid belt today may be seen as a graveyard of planetesimals and embryos that never got the chance to become planets. Each asteroid there is a reminder of the chaotic battles that shaped our solar system's youth. The role of gas in the disk was also crucial in shaping the embryos. As they moved through the dense gas, they felt drag, much like how an airplane feels resistance from the air. This drag slowed their motion and caused them to spiral gradually inward toward the Sun. At the same time, their interactions with the gas could create waves and ripples that changed their orbits. For the embryos, living in this environment meant a constant struggle between growth, collision, and migration. Some embryos migrated closer to the Sun and were lost, while others found stable positions where they could continue growing. The physics of these processes is beautiful in its simplicity, though its effects are grand. Gravity, collisions, and time, all working together, were the forces that sculpted the embryos. Each embryo was like a small kingdom, growing by conquering nearby land and pulling in its neighbours. Eventually, the strongest embryos became the rulers of their regions, sweeping up almost everything around them until only a few major bodies remained. This is how the solar system transitioned from a chaotic swarm of countless objects into a system of a few, well-defined planets. It is breathtaking to realize that Earth itself was once one of these embryos. 4.5 billion years ago, our planet was just a growing body, jostling among others, fighting for survival in the crowded nursery around the Sun. The fact that Earth endured, grew, and eventually became a home for life is the result of countless chance collisions, accidents, and triumphs during this time. Without the stage of planetary embryos, the solar system would still be nothing more than a disk of dust and rubble. The story of planetary embryos also connects to mysteries we are still trying to solve today. For example, why is Mars so much smaller than Earth and Venus? Some scientists think that Mars is a planetary embryo that never grew into a full-sized planet, perhaps because Jupiter's gravity prevented it from gathering enough material. If that is true, then Mars is like a fossil of the embryo stage, frozen in time and giving us a direct glimpse into what those early worlds looked like. Similarly, many moons of the giant planets such as Ganymede or Titan, may have begun as embryos before being captured into orbit around their giant hosts, even beyond our solar system. When astronomers look at young stars surrounded by disks, they are catching glimpses of this very same process happening today. They see gaps in the disks, rings of dust, and hints of growing planets, signs that planetary embryos are forming elsewhere in the galaxy, just as they did here billions of years ago. It is a reminder that the birth of worlds is not a unique story, but a universal one, repeated countless times across the stars. The formation of planetary embryos was a period of both violence and creativity, a time when chaos slowly gave way to structure. Through endless collisions, breakups, and mergers, the solar system forged the seeds of its planets. What began as dust smaller than the width of a human hair grew into mountain-sized rocks, then into worlds the size of Mars, and eventually into the planets we know and live on today. The embryos were the bridge in this journey, the middle step between the smallest pieces of matter and the magnificent planets that orbit the Sun. Gas giants Jupiter and Saturn are the most fascinating and dramatic chapters in the history of our solar system. These enormous planets did not simply appear fully formed. Instead, they grew step by step, starting as small seeds in a swirling disk of gas and dust that circled around the young Sun more than 4.5 billion years ago. What makes them especially interesting is that unlike the rocky planets such as Earth, Mars, Venus, and Mercury, the gas giants are made mostly of light elements like hydrogen and helium. These are the same elements that make up stars, and in a way, Jupiter and Saturn could almost be described as failed stars, because they are massive enough to capture and hold on to thick atmospheres, but not massive enough to ignite nuclear fusion like the Sun. Their formation is tied closely to the environment of the early solar system, and the unique conditions that allowed them to become the kings of planets. When the Sun was still very young, it was surrounded by what scientists call a protoplanetary disk. This disk was made of gas and dust left over from the collapse of a giant molecular cloud. Most of the mass of this cloud went into forming the Sun, but a small portion, only a fraction, was left behind in the disk. This material contained the ingredients that would one day form planets, moons, asteroids, and comets. Close to the Sun, where it was hot, only metals, rocks, and some heavy materials could survive in solid form. Lighter elements such as water, methane, ammonia, hydrogen, and helium existed as gases and could not condense into solid particles. But farther out, beyond what is known as the frost line, temperatures were low enough for ices to form. This line was extremely important because it meant that in the outer regions of the solar system, there were far more solid materials available. Not only could dust grains and rocky particles clump together, but ices of water, carbon dioxide, methane, and ammonia could also form solid bodies. This gave the planets that formed in this region, such as Jupiter and Saturn, a much larger supply of building blocks. The first stage in their formation was very similar to what happened with the rocky planets. Tiny grains of dust and ice stuck together through electrostatic forces, building pebbles, then boulders, and eventually planetesimals, which were objects many kilometers across. These planetesimals collided and merged through gravity, forming planetary embryos. In the inner solar system, these embryos remained relatively small, because there was not enough material around them to grow into something much larger than Earth. But in the outer solar system, where there was far more ice and solid matter, the embryos could grow to sizes several times the mass of Earth. This was the crucial difference. Once these rocky and icy cores reached a critical size, roughly 10 times the mass of Earth, something extraordinary happened. Their gravity became strong enough not only to pull in more solid material, but also to begin capturing gas directly from the surrounding protoplanetary disk. This was the beginning of the runaway process that would transform them into gas giants. The thick gases of hydrogen and helium, which made up most of the disk, began to swirl around these cores and settle into deep, massive atmospheres. As more and more gas fell onto the growing planets, the process accelerated. The more massive they became, the stronger their gravity grew, and the faster they could attract additional material. Within a relatively short time, astronomically speaking, just a few million years, the cores that had started as rocky and icy seeds became truly giant planets. Jupiter was the first to form and also the largest. Today it is more than 300 times the mass of Earth, and more than 1,000 Earths could fit inside its volume. Its core is still thought to be a dense mixture of rock, ice, and metal, but above that lies an envelope of hydrogen and helium that makes up most of its mass. Because it formed so early and grew so quickly, Jupiter acted like a gravitational bully in the young solar system. Its enormous pull affected the orbits of nearby planetesimals and embryos, preventing another planet from forming in the region between Mars and Jupiter. This is why we have the asteroid belt instead of another planet there. Jupiter also scattered many icy bodies outward, helping to populate the Kuiper belt and Oort cloud with comets. In a sense, Jupiter was not just a planet, it was a shaper of the solar system's architecture. Saturn formed soon after Jupiter, though it took a little longer and gathered somewhat less material. It is still enormous, with a mass about 95 times that of Earth, but it is less dense than Jupiter, and even less dense than water. If you could place Saturn in an enormous cosmic ocean, it would float. Like Jupiter, it has a solid or icy core surrounded by a deep atmosphere of hydrogen and helium. The difference in mass and density between the two giants likely came from their slightly different positions in the protoplanetary disk and the timing of their formation. By the time Saturn reached the critical mass to trigger runaway gas capture, the disk was already starting to thin out, and so it captured less material than Jupiter. An interesting point about the gas giants is that they could not have formed if the protoplanetary disk had disappeared too quickly. Observations of young stars in our galaxy show that such disks typically last only a few million years before the gas is blown away by stellar winds or radiation. This meant that Jupiter and Saturn had only a limited window of time to gather their massive atmospheres. If they had not grown large enough before the gas was gone, they would have ended up as smaller icy worlds rather than giants. The fact that they did succeed shows that they formed quickly and efficiently, pulling in vast amounts of material while the opportunity was still there. The atmospheres they captured are remarkable not only for their size but also for their composition. Hydrogen and helium, the most abundant elements in the universe, dominate, making up more than 90% of their bulk. These are the same elements that fuel stars, which is why Jupiter and Saturn are sometimes thought of as star-like planets. If Jupiter had been about 80 times more massive than it is, it could have ignited nuclear fusion and become a star in its own right. In that case, our solar system might have been a binary star system, with 2 suns instead of 1. But as it stands, Jupiter and Saturn are planetary giants, shining only by reflected sunlight and the faint heat of their own formation. Even after they captured their massive atmospheres, Jupiter and Saturn continued to evolve. Their interiors became layered, with pressures so extreme that hydrogen itself was squeezed into exotic states. In Jupiter's deep interior, hydrogen becomes metallic, meaning that the atoms are stripped of their electrons and flow like a liquid metal. This metallic hydrogen is thought to be responsible for Jupiter's powerful magnetic field, which is the strongest of any planet in the solar system. Saturn likely also has metallic hydrogen inside it, though in smaller amounts, which gives it a magnetic field that is weaker but still impressive. The presence of such massive planets had enormous consequences for the rest of the solar system. Jupiter in particular acted as both a protector and a destroyer. On one hand, its gravity could deflect comets and asteroids away from the inner planets, reducing the chances of catastrophic impacts. On the other hand, it could also send dangerous objects on new paths that led them straight into the inner solar system, creating devastating collisions. Some scientists even argue that without Jupiter, Earth might not have had the relatively stable environment that allowed life to flourish. Others suggest that Jupiter's gravity stirred up so much chaos that it prevented the formation of another Earth-sized planet between Mars and Jupiter. Either way, the influence of the gas giants on the history of our planet is undeniable. Saturn too played its part. Its gravity helped shape the outer regions of the solar system, influencing the orbits of Uranus and Neptune and contributing to the structure of the Kuiper belt. Its system of moons, particularly Titan, has drawn great interest because Titan possesses a thick atmosphere and liquid lakes of methane and ethane on its surface, making it one of the most Earth-like worlds beyond our own. These moons are themselves like miniature worlds, born from the leftover material that surrounded Saturn after its formation, just as our moon formed from debris around Earth. Looking at the gas giants today, it is easy to forget the drama of their birth. We see Jupiter with its swirling cloud bands and great red spot, a storm larger than Earth that has raged for centuries. We see Saturn with its breathtaking rings, made of countless icy particles shining in the sunlight. But behind this beauty lies a story of cosmic timing and gravitational power. They are survivors of a chaotic era, the outcome of billions upon billions of collisions, captures, and gravitational dances. Their very existence is proof that the conditions in the young solar system allowed for giants to rise out of dust and gas. The formation of Jupiter and Saturn also raises questions about other planetary systems beyond our own. Astronomers have now discovered thousands of exoplanets around distant stars, and many of them are gas giants. Some orbit extremely close to their stars, in places where we would not expect them to form. These so-called hot Jupiters challenge our understanding because they suggest that giant planets may migrate inward after they form, reshaping their systems in dramatic ways. Studying our own gas giants, therefore, not only tells us about our history, but also helps us make sense of the bewildering variety of worlds in the galaxy. Given the right conditions, an abundance of solid material beyond the frost line, a supply of gas in the protoplanetary disk, and enough time before that gas disappeared, giant planets could almost be expected to form. But the exact details, their masses, their positions, their effects on other planets, depended on countless accidents of timing and dynamics. The result in our case was two majestic giants that continue to dominate the outer solar system, guardians and rulers of a realm far beyond the warmth of the sun. Their creation was not quick or simple. It was a story that took place over millions of years, with every step shaped by invisible forces of gravity and motion. From tiny grains of ice and dust to worlds of unimaginable size, Jupiter and Saturn are proof that even the mightiest structures in the universe can begin with the smallest of seeds. The capture of their massive atmospheres was the turning point that made them what they are today. Colossal planets that will continue to orbit the sun for billions of years to come, long after humanity is gone, silent witnesses to the deep history of the cosmos. In the history of the cosmos, how the inner planets of our solar system came to life is one of the most fascinating tales. Mercury, Venus, Earth, and Mars, the four small rocky worlds that orbit closest to the sun, did not exist in the beginning. They were not carved fully formed out of stone, nor were they suddenly placed in orbit by some instant act of creation. Instead, they grew slowly, step by step, over millions of years, out of dust, gas, and countless collisions. Their birth is like the story of building a house, except instead of bricks and wood, the builders were cosmic dust grains, rocks, ice, and molten metal, all dancing and colliding in the great swirling disk that surrounded the young sun. To understand how Mercury, Venus, Earth, and Mars came to be, one must picture not only violent crashes and fiery heat, but also gentle gatherings of particles, slow shaping of orbits, and the delicate balance of cosmic forces. When the sun was still very young, less than a few million years old, it was not alone in space. Around it spun a huge flattened cloud of dust and gas. This cloud is what astronomers call the protoplanetary disk. It stretched across billions of kilometers, with the densest part lying near the sun, and the thinner parts extending outward toward the distant edges where the giant planets would later form. Within this disk were countless tiny particles, many no bigger than grains of sand mixed with gas. At first these particles simply swirled, colliding lightly and bouncing apart, but as time went on, something remarkable happened. Instead of always bouncing, some particles began to stick together, held by tiny forces of attraction. Slowly, dust turned into pebbles, pebbles grew into rocks, and rocks became boulders. This was the very first step in the long chain of events that would eventually create planets. The region close to the sun, where Mercury, Venus, Earth, and Mars would be born, was very different from the outer parts of the disk. Because of the sun's powerful heat, the inner disk was far too hot for volatile materials like water and methane to survive as ice. Instead, only metals and rocky minerals could exist in solid form. This is why the terrestrial planets are rocky worlds, made mostly of silicate minerals and iron, while the outer planets are filled with lighter gases and ices. In a sense, the sun itself determined the ingredients from which each planet could be built, simply by the heat it gave off. The inner planets were destined to be rocky from the start. As rocks and boulders continued to grow, they began to collide more strongly. Some shattered, but others merged, forming larger bodies called planetesimals. These planetesimals were like miniature worlds, ranging from a few kilometers across to hundreds of kilometers in diameter. They were numerous, filling the inner solar system like a great swarm of asteroids. Every orbit around the Sun brought new opportunities for collisions. The larger a planetesimal became, the stronger its gravity grew and the more it could attract smaller neighbours. This process is called accretion, and it is the engine of planet building. Over time, a few planetesimals grew far larger than the rest. These were the planetary embryos, bodies as large as the Moon or even larger. They cleared paths through the disk, gathering up material and colliding with other embryos. It was during this chaotic age, lasting tens of millions of years, that the foundations of Mercury, Venus, Earth and Mars were set. The collisions between embryos were often cataclysmic. Imagine worlds smashing into each other at tens of kilometers per second, releasing energy equal to millions of nuclear bombs. Some impacts tore bodies apart while others merged them into larger planets. Mercury, the smallest of the terrestrial planets, is thought to be the result of such a violent history. One leading idea is that Mercury was once a larger body with a thick rocky mantle, but a massive collision with another embryo stripped away much of that outer layer, leaving behind a dense metal-rich core and a relatively thin shell of rock. This is why Mercury today has such a high proportion of iron compared to rock, making it the densest planet in the solar system after Earth. Its small size and thin atmosphere are scars left behind by the violence of its birth. Venus and Earth, in contrast, grew much larger. They were in a region of the solar system where there was more material available, and their orbits allowed them to collect more planetesimals. As they grew, they also experienced giant impacts. The most famous of these is the impact that created Earth's moon. According to the giant impact hypothesis, a Mars-sized body, often called Theia, struck the young Earth about 4.5 billion years ago. The collision was so massive that much of Earth's outer layers were blasted into orbit, where the debris gathered and formed the moon. This single event not only gave Earth its companion, but also reshaped Earth's surface and tilted its axis. Without that impact, Earth as we know it today might not exist. Venus, Earth's sister planet in size and composition, may also have experienced giant collisions, though its history remains more mysterious because of the thick blanket of clouds that hides its surface. Still, its size and density suggest it went through a similar process of growth and accretion. Unlike Earth, however, Venus never developed plate tectonics as we know them, and it lacks a large moon. These differences, though subtle at first, would eventually lead Venus down a very different path of evolution, turning it into a world of crushing pressure and runaway greenhouse heat. Mars, the last of the four, presents another puzzle. Compared to Venus and Earth, Mars is much smaller, only about half the diameter of Earth. For many years, scientists wondered why Mars did not grow larger, since it was also in the inner solar system. One possibility is that Mars was unlucky in its location. It formed near the boundary of the inner and outer solar system, where the powerful gravity of the giant planet Jupiter stirred up the orbits of planetesimals. Jupiter's presence may have scattered away much of the material that Mars could have used to grow larger, leaving it stunted. Thus, Mars became a planet that is smaller than Earth, with a thinner atmosphere and weaker gravity, characteristics that would eventually make it less hospitable to life. During the early years of the terrestrial planets, the entire inner solar system was still a violent place. Countless leftover planetesimals, asteroids and comets continued to bombard the young worlds. This era, known as the Late Heavy Bombardment, may have lasted hundreds of millions of years. It scarred Mercury with craters, gave Mars its ancient basins, and reshaped the surfaces of Venus and Earth again and again. But as time passed, most of the debris was swept up, either colliding with the planets or being flung out into distant orbits. By around 4 billion years ago, the bombardment slowed, and the planets began to settle into the more stable system we recognize today. Yet the story of their birth was not only about collisions and impacts. As these planets grew, they also began to differentiate inside. This means their materials are separated by density, with heavy metals like iron sinking to the core and lighter silicate rocks rising to form mantles and crusts. Differentiation gave Earth its iron core, which would later power its magnetic field. It gave Venus and Mars their layered structures as well, Mercury's differentiation was extreme because so much of its lighter material had been stripped away. In these ways, the planets developed their internal architecture during their infancy. The atmospheres of the terrestrial planets also began to take shape in this time. At first, none of them had the kind of air we could breathe. Their early atmospheres came from volcanic eruptions, releasing gases trapped inside their interiors. Carbon dioxide, nitrogen, sulfur compounds, and water vapor filled the skies. Earth eventually developed conditions that allowed liquid water to remain on its surface, while Venus became choked with carbon dioxide, and Mars lost much of its air to space. The differences between them were rooted in the same processes that governed their birth: their size, distance from the Sun, and violent histories of collision. Earth, in many ways, became the lucky one among its siblings. Its size was just right to hold onto an atmosphere and support liquid water. Its distance from the Sun was neither too hot nor too cold. Its moon stabilized its tilt, preventing wild swings in climate. These fortunate circumstances, born out of cosmic accidents and violent events, allowed Earth to become a cradle for life. Venus, in contrast, grew into a suffocating furnace, and Mars became a frozen desert. Mercury remained a barren rock scorched by the sun. All four were built by the same process, but their final destinies diverged in dramatic ways. When we think about the birth of the terrestrial planets, it is easy to imagine it as a linear story, but in reality it was messy, chaotic, and full of chance. Tiny variations in where a planetesimal formed, or when a collision happened, could change everything. If Earth had not been struck by Theia, it might not have a moon. If Jupiter had formed slightly closer, Mars might not exist at all. The solar system we live in today is only one of many possible outcomes that could have arisen from the swirling disk of dust around the young Sun. Today, astronomers have discovered thousands of planets around other stars, and many of them are rocky worlds like the terrestrial planets. Some orbit so close to their stars that they are even hotter than Mercury, while others circle farther out, perhaps more like Mars. By studying how our own rocky planets were born, we gain insight into the possible fates of these distant worlds. Some may be barren, some may be hostile, but perhaps a few, like Earth, may have the right combination of circumstances to nurture life. The Moon, the glowing companion of our Earth that has guided people through countless nights, holds a story of birth that is as dramatic as it is mysterious. To understand how the Moon came into being, we must travel back in time not just millions of years, but billions. We must imagine our Earth in its infancy, a very young planet in a chaotic solar system that had only just formed. The Earth of those days was not the calm and stable world we know now. It was wild, violent, and dangerous, a place where gigantic rocks and blazing chunks of material from the birth of the solar system still roamed freely, colliding with young planets and leaving scars. Among all the ideas that scientists have proposed about how the Moon was born, one theory stands tall above the rest: the giant impact theory. This idea tells us that the Moon is the product of a colossal, catastrophic collision that changed the destiny of Earth forever and gave us the bright satellite that has inspired myths, art, poetry, and science for thousands upon thousands of years. To truly picture this story, let us set the stage. The solar system formed about 4.5 billion years ago, when a swirling cloud of gas and dust collapsed under gravity and gave birth to the Sun at its centre. Around the young Sun, leftovers of dust and rock clumped together, growing larger over millions of years to form planets. But this was no neat and orderly process. The early solar system was more like a battlefield, full of collisions, near misses, and violent crashes. Planets were still forming, and their surfaces were constantly being reshaped by impacts from planetesimals, which were smaller bodies of rock and ice that filled space like wandering bullets. Earth, at that time, was one of many worlds trying to find stability, and it was still molten in many places, its surface covered in fiery lava and bubbling with volcanic activity. It was during this chaotic age that a fateful encounter occurred. Scientists believe that about 4.5 billion years ago, when Earth was still very young, it was struck by another planet-sized body. This intruder is thought to have been about the size of Mars, much smaller than Earth, but still unimaginably massive. It is often called Theia, a name borrowed from ancient Greek mythology, after the Titaness who was the mother of Selene, the goddess of the moon. The collision between Earth and Theia was no ordinary crash. It was a titanic impact, so powerful that it released more energy than any event since the birth of the solar system itself. Imagine Earth spinning in space, its young crust partly molten, when Theia hurtled toward it at great speed. The two worlds collided in a cataclysm that would have melted rock, boiled oceans, and shaken the planet to its core. A huge portion of the Earth's outer layers, along with much of Theia itself, was blasted into space in a gigantic explosion. Vast amounts of molten rock, vaporized material, and fragments of Earth's mantle were thrown into orbit around the planet, forming a fiery ring of debris. This glowing halo of broken rock circled Earth, held by gravity but restless and chaotic. Over time, this debris began to come together, pieces colliding and merging under their own gravity until they formed a single large body, the Moon. This dramatic beginning is what the giant impact theory suggests. It explains not only the Moon's size and orbit, but also its composition. For years, scientists puzzled over why the Moon's rocks look so similar to those of Earth, yet not exactly the same. When astronauts from the Apollo missions brought back lunar samples in the late 1960s and early 1970s, scientists studied them carefully. They found that the Moon's rocks were made of the same kinds of elements found in Earth's mantle, but the ratios of certain isotopes, like oxygen isotopes, were almost identical to Earth's. This was a strong clue that the Moon had been made from Earth's own material, not captured from somewhere else. At the same time, the Moon was missing certain elements that evaporate easily, which fit the idea that the Moon was born out of a superheated, violent process where lighter elements boiled away. The giant impact theory answers many questions, but it also sparks the imagination. Picture that glowing ring of molten rock around Earth, like Saturn's rings but far hotter and more unstable. Piece by piece, chunks of molten stone smashed into one another, sticking together, cooling, and slowly forming a sphere. Gravity pulled the newborn Moon into shape, and over the course of millions of years, it settled into its orbit around Earth. At first, the Moon was much closer to our planet than it is today. It would have looked enormous in the night sky, filling it with a breathtaking view. Over billions of years, tidal forces between Earth and the Moon caused the Moon to drift slowly away, to the distance we see now, about 238,000 miles from Earth. Even today, the Moon continues to inch farther from us, moving about 1.5 inches away each year. The creation of the Moon changed Earth forever. Without the Moon, life on Earth might have taken a very different path. The Moon stabilizes Earth's tilt, which keeps our climate relatively steady over long stretches of time. Without this stability, Earth's axis could wobble wildly, leading to chaotic shifts in climate that would have made it much harder for complex life to thrive. The Moon also creates tides by pulling on Earth's oceans with its gravity. These tides may have been vital in the early development of life, stirring the oceans and helping primitive life forms to adapt and evolve. The Moon, born from destruction, became a guardian and guide for life on Earth. For centuries, people created myths and stories to explain the Moon's presence. Some cultures saw it as a goddess, others as a god, a rabbit, or a face watching from above. But only in the modern era did humans begin to understand its true origins. The journey to that knowledge took centuries of observation, theories, and finally, direct exploration. When the Apollo astronauts set foot on the Moon in 1969, they gave humanity the first chance to hold pieces of our satellite in our hands and study them. These rocks were the key that unlocked the mystery of the Moon's birth, supporting the idea that it was not captured by Earth and not formed alongside Earth in the same orbit, but instead was born out of one of the most violent impacts in planetary history. The giant impact theory, though widely accepted, still leaves some mysteries unsolved. For example, if Theia collided with Earth, scientists would expect to find some chemical fingerprints of this other body in the Moon's rocks. But so far, the evidence suggests that the Moon's material is almost entirely like Earth's. This raises the question, did Theia and Earth already share a similar composition, because they were born from the same region of the solar system? Or did the collision mix their materials so thoroughly that no trace of Theia remains distinct? These are questions that scientists continue to explore, using advanced computer simulations and more detailed analysis of lunar samples. Another puzzle is the exact mechanics of how the debris from the collision came together. Did the Moon form quickly, in just a few years, as molten rock clumped together in orbit? Or did it take thousands, even millions of years, with pieces slowly joining to create a stable body? Some scientists suggest that the Moon may have formed not as a single object at once, but as multiple smaller moons that later merged to become the one we see today. Such ideas show that the story of the Moon's birth is still being refined, and each new discovery adds depth to the tale. Regardless of the details, the giant impact theory paints a picture of creation through destruction, of beauty born from chaos. The Moon we see shining so calmly above us is a survivor of violence on a scale we can hardly imagine. It reminds us that the universe is both dangerous and creative, shaping worlds through fire and collision. Every time we look at the Moon, we are looking at a piece of Earth itself, a fragment of our planet's own body that was flung into space and then became a companion for billions of years. Over time, the Moon cooled and its surface became solid. The dark patches we see today, called Maria, are vast plains of solidified lava, created by volcanic eruptions billions of years ago when the Moon's interior was still hot and active. The brighter highlands are older and covered with craters from impacts that battered the Moon during the heavy bombardment period, a time when countless asteroids and comets rained down on the inner solar system. Unlike Earth, the Moon has no atmosphere to protect it, no weather to erase scars, and no plate tectonics to recycle its surface. This means that every crater, every scar from billions of years ago still remains visible, a record of the solar system's violent history. The Moon's face, as we know it, is thus like a time capsule. When we look at it, we see not only the story of its own creation, but also a record of the chaos that shaped the solar system. And because the Moon was born from Earth, its story is deeply tied to ours. The collision that created it may have been destructive, but it also gave Earth the stability and conditions needed for life to flourish. Without that impact, without the birth of the Moon, we might not even be here to tell the tale. Scientists today continue to study the Moon with new tools. Space missions from many countries have orbited, landed, and even returned samples. Each mission adds new details, confirming some parts of the giant impact theory while challenging others. In the future, humans may return to the Moon not only to explore, but also to build bases and use it as a stepping stone to further adventures in space. When that happens, people will be walking on a world that is both foreign and familiar, a world that is quite literally a piece of our Earth, a piece torn from our planet in an ancient collision that still echoes in the skies above. Long ago, in the very early years of the solar system, the young planets and moons did not yet enjoy the quiet, steady paths they follow today. They were worlds still raw and unfinished, scarred and battered by storms of stone and ice that roared across the skies. This chaotic period is remembered in science as the late heavy bombardment. It was a time when enormous amounts of rocky debris and icy bodies swept through the inner solar system and rained down on the young planets and moons with tremendous force. The energy released by these impacts was beyond imagination, reshaping entire surfaces, melting vast regions, and perhaps even stirring the very chemistry that would one day lead to life. The story of the late heavy bombardment begins with the leftovers of creation itself. When the Sun first formed from a collapsing cloud of gas and dust, about 4.5 billion years ago, the swirling material around it began to gather into planets. But the birth of planets was not a neat and tidy process. Billions upon billions of rocky fragments, icy lumps, and metallic pieces circled the Sun, colliding, merging, and breaking apart in endless violence. Over tens of millions of years, the larger planets cleared most of their paths, sweeping up material with their gravity or ejecting it into far-off orbits. Yet not everything was swept away. Vast amounts of debris still lingered, especially in the regions beyond the gas giants. Scientists believe that the late heavy bombardment struck around 3,900,000,000 years ago, several hundreds of millions of years after the Earth, the Moon, and their neighbours first formed. For reasons that are still being studied, the inner solar system suddenly found itself under siege once again. Gigantic waves of asteroids and comets came crashing inward, colliding with the terrestrial planets and their moons. On Earth, enormous craters were gouged out, mountains were shattered, and whole seas may have boiled from the heat of the impacts. On the Moon, which has no atmosphere to erase such scars, the craters and dark basins we see today tell the tale of that ancient bombardment more clearly than anywhere else. The evidence of this dramatic era comes mostly from the Moon. When astronauts from the Apollo missions brought back samples of lunar rocks, scientists discovered something extraordinary. Many of the rocks taken from the large dark plains known as Lunar Maria showed that they had been melted around the same time, roughly 3,900,000,000 years ago. This pointed to a concentrated period of impacts rather than a slow trickle of collisions spread evenly over billions of years. The Moon's heavily cratered surface acts like a time capsule, preserving the scars of events that on Earth would have been long erased by wind, water, and the movements of continents. But what caused this sudden surge of impacts? The leading idea is tied to the restless movement of the giant planets Jupiter and Saturn. In the early solar system, these colossal worlds did not sit exactly where they do today. Their orbits gradually shifted due to gravitational tugs between them and with countless smaller icy bodies beyond Neptune. According to one widely accepted scenario, sometimes called the Nice model, after the city in France where it was developed, Jupiter and Saturn entered into a special gravitational dance about 700 million years after the Sun was born. They reached a point where Jupiter orbited the Sun twice for every orbit Saturn completed. This resonance destabilized the orbits of Uranus and Neptune, pushing them outward into the icy disk of comets and planetesimals beyond. The disturbance scattered a vast swarm of objects throughout the solar system. Many were flung out entirely, but countless others were sent hurtling inward, where they slammed into the inner planets and moons. The violence of the late heavy bombardment cannot be overstated. Imagine asteroids tens or even hundreds of kilometers wide striking planets at speeds of tens of kilometers per second. The energy of a single large impact was equal to millions of nuclear bombs exploding all at once. Each collision could dig a crater hundreds of kilometers across, melt rock into seas of lava, and send debris flying around the world. On Earth, some of the largest impacts may have temporarily vaporized oceans and heated the atmosphere until the surface glowed red. Life, if it had already begun, would have faced challenges nearly impossible to survive. Yet paradoxically, the same destruction may have also sown the seeds for life's eventual flourishing. The impacts may have delivered water, carbon compounds, and other essential ingredients. They also created hydrothermal systems around the craters, warm watery environments where chemical reactions could have produced the first simple living molecules. On the Moon, the marks of this era remain frozen in time. The great dark basins known as Mare Imbrium, Mare Serenitatis, Mare Crisium, Mare Nectaris, and others are thought to have formed during this bombardment. Each one is hundreds of kilometers wide, the result of titanic impacts that melted enormous volumes of lunar rock. Later, these basins were flooded by lava that welled up from the Moon's interior, leaving the flat, dark plains we see with the naked eye. These scars are reminders of the immense violence that shaped not only the Moon but the entire inner solar system. On Mars, evidence suggests the same bombardment struck hard. The southern highlands of Mars are covered in craters, some of which date back to this time. Vast basins such as Hellas Planitia, nearly 2,000 kilometers wide, may be products of the same violent wave of impacts. Mars, too, may have seen its climate altered repeatedly by these collisions, as huge clouds of dust and vapor were blasted into the atmosphere, changing temperatures and perhaps even affecting the presence of liquid water. Venus, with its thick, choking atmosphere, hides its scars more effectively. The surface we see today has been resurfaced by volcanic activity in more recent geological times, but scientists suspect Venus was also battered during the bombardment. Any ancient craters from that period are likely buried or erased, yet its history must have been just as violent as Earth's and Mars's. On Earth itself, almost no clear evidence of the bombardment remains. Our planet's surface is constantly reshaped by plate tectonics, erosion, and the cycle of oceans and atmosphere. Ancient craters that may once have existed were long ago erased. Only a few traces, hidden deep in ancient rocks, hint at the possibility of impacts from that time. Tiny mineral grains called zircons, some of the oldest materials on Earth, show signs of having been heated by intense events about the same age as the bombardment. These faint clues, combined with the more obvious lunar record, convince scientists that Earth too was hammered mercilessly. The consequences for early life on Earth are one of the most fascinating parts of this story. If life had already started by 3,900,000,000 years ago, the bombardment may have nearly wiped it out more than once. Some scientists imagine a scenario in which the surface of Earth was sterilized repeatedly, with only hardy microbes deep underground surviving the fiery impacts. In this view, life clung on in hidden refuges until conditions calmed. Others think that life may not have started until after the bombardment, in the quieter environment that followed. In either case, the bombardment shaped the conditions under which our planet became habitable. It might have provided the final push needed for complex chemistry to take hold. The late heavy bombardment also had long-lasting effects on the structure of the planets themselves. The impacts broke apart crusts, stirred interiors, and left behind basins that later filled with lava or water. They may have influenced the magnetic fields of some planets by altering how their cores cooled. They certainly played a role in delivering or redistributing volatile elements such as water and carbon dioxide. Without such a bombardment, the planets might look very different today. There is still debate among scientists about the exact nature of this event. Some argue that instead of a sudden spike of impacts, the inner planets may have simply experienced a gradual decline in collisions over hundreds of millions of years. In this view, the evidence from the Moon might reflect a sampling bias, since Apollo astronauts mostly visited certain regions. Others maintain that the clustering of dates in lunar samples is real and points to a genuine surge in impacts. The discussion continues, with new data from lunar missions, computer simulations, and studies of asteroids helping to refine the picture. Regardless of the details, the late heavy bombardment remains one of the most dramatic episodes in planetary history. It was a storm of rock and ice on a scale we can barely imagine, a storm that battered every world from Mercury to the outer moons. The scars of that storm are still written across the surfaces of countless bodies in the solar system. Every crater we see on the Moon with our eyes, every pitted surface of an asteroid glimpsed by spacecraft, and every battered moon of Jupiter and Saturn carries whispers of that ancient time. To truly picture it, imagine standing on the surface of the young Moon during the bombardment. The sky would not have been peaceful or quiet. Instead, giant fireballs would have flared again and again as asteroids slammed down. The ground would have trembled like an earthquake with each impact. Dust and molten rock would have filled the thin sky, glowing red with heat. Lava would have poured across the surface, filling basins with rivers of fire. The bombardment was not a single day or year of terror, but a long era stretching over tens of millions of years. Worlds were remade in that crucible of stone and fire. Even after the main wave of impacts slowed, collisions never stopped entirely. Cratering has continued throughout the solar system's history, though at a far lower rate. The craters of later eras sit on top of the older scars, layering history upon history. Yet the late heavy bombardment stands out as a unique moment when the violence peaked and left a lasting imprint on all the inner planets and moons. In many ways, we owe our existence to this storm. Without it, Earth might not have received the right balance of water and carbon to sustain life. Without it, the crust of Earth might not have been broken and renewed in ways that allowed oceans and continents to develop. Without it, perhaps life would never have found its foothold. The bombardment was both destroyer and creator, an event that shows how intimately violence and creation are tied in the history of worlds. As we study other planetary systems around distant stars, we sometimes catch glimpses of similar bombardments happening elsewhere. Disks of dust and debris around young stars may be signs of worlds being hammered by the remnants of their formation. In those distant collisions, we may be watching the same process that once shaped our own Earth and Moon. It is a reminder that what happened here is part of a universal story, repeated countless times across the galaxy. The late heavy bombardment teaches us that creation is rarely gentle. Worlds are forged in fire, ice and stone, beaten into shape by cosmic hammers. Yet from that chaos can emerge the delicate balance that allows oceans to form, continents to rise, and eventually life to appear. The craters we see when we look at the Moon are not just scars. They are symbols of survival, reminders of the storms our world endured before becoming the home we know. The memory of this ancient time lives on in every rocky surface of the solar system, in the dark plains of the Moon, the craters of Mercury, the scarred highlands of Mars, and the battered moons of the gas giants. It is written in the minerals of ancient rocks and in the chemistry of our oceans. It is part of the very fabric of Earth's story. Asteroids, comets, and Kuiper Belt objects are like time capsules left behind from the dawn of our solar system. They are not simply scattered rocks or frozen balls of ice drifting in space, but the surviving pieces of an ancient puzzle that tell us about the earliest days when planets were still forming. To look at them is almost like looking backward through billions of years, peering into a story written in stone, ice, and dust. These small bodies did not grow large enough to become planets, yet they hold within them the very same materials that once swirled around the young sun and eventually came together to create worlds like Earth, Mars, and Jupiter. Because they remained small and untouched for most of cosmic history, they preserve the raw ingredients and early conditions of our planetary neighbourhood in a way that larger, geologically active planets no longer can. When the solar system was young, more than 4.5 billion years ago, it was a place of chaos and growth. A great cloud of gas and dust collapsed under gravity to form the Sun, and the leftover material flattened into a spinning disk known as the Protoplanetary disk. Inside this whirling structure, tiny grains of dust began to stick together, forming clumps, then larger and larger bodies that astronomers call planetesimals. Some of these grew to enormous sizes and became the rocky planets of the inner solar system and the gas giants farther out. But not every fragment managed to combine into a planet. Many pieces were left behind, pushed aside, or trapped in distant orbits. Those survivors are the asteroids, the comets, and the icy Kuiper Belt objects that remain today as silent witnesses of a time when everything was still being built. Asteroids, for example, are often described as space rocks, but they are far more interesting than that simple phrase suggests. They are mainly made of metal and stone, ranging from small pebbles to bodies hundreds of kilometers wide. The largest of them, called Ceres, is big enough to be considered a dwarf planet, and it alone contains a huge portion of the total mass of the asteroid belt. The belt itself lies between Mars and Jupiter, and its very existence tells us something important about the history of planetary formation. Jupiter's enormous gravity disrupted the material in this region, preventing it from gathering into a single large planet. Instead, what we have today is a scattered population of countless fragments, leftovers of what might have been another world. By studying asteroids, scientists can investigate what the building blocks of rocky planets were like before they fused together into spheres like Earth. Some asteroids are made mostly of metal, rich in iron and nickel, suggesting that they could be pieces of ancient protoplanets whose outer layers were stripped away in colossal collisions, leaving behind exposed cores. Others are carbon-rich, dark and primitive, containing organic compounds that might resemble the same chemical ingredients that helped life begin on Earth. Still others are stony and bright, resembling the crusts of larger planetary embryos that never fully matured. Each asteroid is like a different page in a book of planetary history, each one telling a different chapter about formation, destruction, and survival in the early solar system. Comets, on the other hand, are the icy nomads of space. They are made of frozen water, carbon dioxide, methane, and ammonia, mixed with dust and rock. These fragile objects spend most of their time far away in the cold outer reaches of the solar system, but occasionally their orbits bring them close to the Sun. When that happens, the heat causes their ice to vaporize, releasing streams of gas and dust that form the glowing coma and tail that make comets so spectacular to see in the sky. Ancient cultures often looked upon comets as omens or messengers, bright streaks of light that suddenly appeared and faded away. Today, however, we see them as scientific treasures, frozen samples from the birth of the solar system. Comets likely carry some of the same volatile materials that were present in the outer protoplanetary disk billions of years ago. Some scientists believe that during the early bombardment of Earth, comets may have delivered water and organic molecules that contributed to the conditions needed for life to arise. Their icy composition has remained mostly unchanged for eons, shielded by the coldness of deep space, making them some of the most pristine relics from the solar system's infancy. To watch a comet pass by is to witness an object that has journeyed since ancient times, carrying in its frozen heart the story of how the Sun and planets came to be. Even farther away than the comets that we see regularly is an enormous region called the Kuiper Belt. This is a vast ring of icy objects that begins beyond the orbit of Neptune and stretches outward for billions of kilometers. The Kuiper Belt is home to countless small frozen bodies, as well as some larger ones that rival or exceed Pluto in size. These objects, sometimes called trans-Neptunian objects, represent the remnants of the outer disk that never managed to form into full planets. Just as Jupiter's gravity disrupted the asteroid belt, Neptune's gravity influenced the orbits of many Kuiper belt bodies, scattering them into resonances or sending them outward into the deep dark of interstellar space. The Kuiper belt is fascinating not only because of its icy population, but also because it is essentially a fossil of the solar system's edge. Here lie bodies like Pluto, Haumea, and Makemake, which are now officially classified as dwarf planets. Their surfaces are coated with frozen nitrogen, methane, and other exotic ices that can change directly from solid to gas under sunlight, creating thin atmospheres. Some of these worlds even show hints of geological activity, such as cryovolcanoes that erupt with slush instead of lava, suggesting that the outer solar system is more dynamic than we once imagined. Each Kuiper belt object holds secrets about the chemistry and physics of planet building at extreme distances from the Sun. Together, asteroids, comets, and Kuiper belt objects form a kind of cosmic archive. They record what conditions were like when the solar system was first forming, and they help us understand how planets like Earth came to exist. They are survivors of a violent and crowded era, when collisions were frequent and planetary embryos were smashing into one another, growing, breaking, and reforming. While the planets went on to develop atmospheres, oceans, mountains, and life, these smaller bodies mostly remained unchanged. That is why they are so important. They offer us samples of the past that the larger evolving worlds can no longer provide. Over the centuries, humanity's fascination with these objects has grown. In ancient times, comets terrified or inspired people with their sudden appearances. Later, astronomers like Galileo and Newton began to understand their true nature as part of the solar system. In the 19th century, careful observations revealed the existence of the asteroid belt, and in the 20th century Pluto and other distant icy bodies were discovered, opening the door to the study of the Kuiper belt. In recent decades, spacecraft have flown past asteroids, landed on them, and even returned samples to Earth. We have also sent missions to study comets up close, such as the European Space Agency's Rosetta mission, which followed Comet 67 Churyumov-Gerasimenko, and even deployed a lander onto its surface. These explorations are like archaeology on a cosmic scale, collecting evidence from the earliest chapter of planetary history. One of the most striking things about these remnants of formation is their sheer variety. Some asteroids are smooth and rounded, while others are jagged and irregular. Some are solid chunks of rock, while others are loose piles of rubble held together only by their weak gravity. Some comets are bright and active, sprouting long tails, while others barely show activity at all. In the Kuiper belt, some objects spin rapidly, some are stretched into odd shapes, and some have tiny moons of their own. This diversity tells us that the process of planetary formation was messy and complex, filled with collisions, disruptions, and rearrangements that left behind a wide range of survivors. Beyond the Kuiper belt lies the hypothetical Oort cloud, an enormous spherical shell of icy bodies that extends far into interstellar space. While we cannot yet observe it directly, astronomers believe it exists because of the orbits of long-period comets that come from very distant regions. If the Oort cloud is real, then it is the most distant reservoir of primordial material, a place where icy planetesimals were thrown by the gravity of the giant planets billions of years ago and have remained ever since, barely touched by time. To imagine the Oort cloud is to picture the solar system not as a neat arrangement of planets, but as a vast and layered structure, surrounded by countless small remnants that preserve its history. The importance of studying asteroids, comets, and Kuiper belt objects is not only historical but also practical. Some asteroids pass close to Earth, and their potential to impact our planet reminds us that the story of planetary formation is not finished. In fact, impacts from such bodies played a central role in shaping the planets and moons, and they still pose a threat today. But at the same time, these bodies may also represent future resources, containing metals, water, and other materials that could support human exploration of space. Mining asteroids or harnessing the resources of comets may one day help humanity expand beyond Earth, turning these relics of the past into stepping stones toward the future. To appreciate these remnants is to realize how extraordinary the solar system really is. Imagine standing on the surface of a small asteroid, seeing the stars above you with no atmosphere to blur their light, knowing that you are standing on a fragment that has existed since before Earth itself had an ocean. Or picture flying alongside a comet as it approaches the sun, watching jets of vapour burst from its surface, glowing like a ghostly torch across the night sky. Or imagine exploring the frozen plains of Pluto, where mountains of water ice rise like jagged cliffs, and nitrogen glaciers crawl slowly across the surface under the pale light of a distant sun. Each of these experiences would be like walking into a living museum of creation. Gravity is one of the most mysterious and yet one of the most powerful forces in the universe. It cannot be seen directly, it cannot be touched, and it cannot be turned on or off like a light switch. Yet without it, the universe as we know it would not exist. Planets would not circle stars, moons would not travel around planets, galaxies would not hold themselves together, and stars themselves would not even form in the first place. Everything that we see in the skies above us, and everything that makes up our home, the Earth, has been shaped, held, and balanced by gravity. One of the most remarkable stories about gravity is how it guided and stabilized the orbits of planets in the early solar system. This story stretches back billions upon billions of years, into the time when the young sun was just beginning to shine and the planets were still in the process of finding their permanent paths around it. In the beginning, the solar system was not an orderly place at all. Instead of planets moving smoothly around the sun in neat, predictable paths, the early solar system was a turbulent and chaotic environment. Imagine a giant disk of gas and dust spinning slowly in space. From this disk, which scientists call the Protoplanetary disk, everything in our solar system was born. At first, there were only small pieces of matter, tiny grains of dust, and clumps of gas. These pieces moved about, colliding with each other, sticking together sometimes and breaking apart other times. Over millions of years, these small grains became larger clumps, then rocky bodies, and eventually planetesimals, which were the seeds of planets. But even when the first true planets began to grow, they did not yet have stable orbits. They were pulled by the gravity of the sun, by the gravity of each other, and by the gravity of countless smaller pieces of debris still flying around in the disk. Gravity in this early stage acted like both a sculptor and a destroyer. On one hand, it brought together smaller bodies, pulling them into larger ones and helping to build the planets. On the other hand, it also caused countless violent collisions. Young planets often crashed into one another, shattering into fragments or merging into larger bodies. Some were thrown out of the solar system entirely, flung into the cold emptiness of space by the gravitational tugs of the larger worlds. Others fell into the sun and were consumed. The solar system in these early days was a place of endless battles, with gravity deciding who would survive and who would be lost. As time passed, the most massive planets began to assert dominance. The sun, being by far the heaviest object in the solar system, had the strongest pull of all. Everything circled around it, though not yet in the calm and steady way we see today. Instead, the orbits of the young planets were stretched, tilted, and often unstable. Sometimes two planets would come close to one another, and their mutual gravity would change their paths dramatically. For example, if a smaller planet passed near a larger one, it could be flung into a more distant orbit, or even thrown completely away from the sun. This process, known as gravitational scattering, played a huge role in shaping the early solar system. The giant planets, Jupiter and Saturn especially, had enormous influence. Jupiter, the most massive planet in the solar system, has more than 2 times the mass of all the other planets combined. Its gravity was like a giant hand stirring the early disk. Asteroids that came too close to Jupiter were pulled apart, redirected, or ejected. This is why the asteroid belt between Mars and Jupiter never formed into a planet. Jupiter's gravity kept stirring it up, preventing the smaller bodies from merging into something larger. Saturn, Uranus, and Neptune also played their parts, tugging on each other and on the smaller bodies, gradually shaping the orbits into the system we see today. One of the most fascinating aspects of this story is how the orbits of the planets eventually settled into stable paths. Stability did not come quickly. For tens of millions of years, the planets continued to shift, collide, and scatter debris. But over time, the violent phase gave way to a calmer one. Why did this happen? The answer again lies in gravity. While gravity caused chaos in the beginning, it also has a natural tendency to seek balance. Planets that moved in unstable paths often ended up being removed from the system, either by crashing into others or being thrown out into deep space. The survivors were those that found orbits where their gravitational pulls did not lead to endless disruption. These survivors gradually adjusted their paths until they reached a kind of harmony. This harmony is not perfect, but it is strong enough to last for billions of years. Today, the planets of our solar system move in nearly circular paths around the Sun, staying in their lanes and rarely causing trouble for each other. The Earth, for example, circles the Sun once every 365 days, keeping almost exactly the same distance from it year after year. Mercury, Venus, Mars, and the outer planets do the same, each with its own rhythm. This balance is what allows life to exist on Earth. Without stable orbits, planets would wander too close to the Sun and burn up, or too far away and freeze. Stability gave our world the steady conditions it needed for oceans, air, and living creatures to form. An interesting part of this balancing act is what scientists call resonances. A resonance happens when two planets or moons move in orbits that are related by simple numbers. For example, one moon might circle its planet twice while another moon circles once. This creates a repeating pattern where the gravitational pulls line up regularly, like dancers keeping in rhythm with each other. Resonances can make orbits more stable, or, in some cases, more unstable. In our solar system, there are many examples. The moons of Jupiter, such as Io, Europa, and Ganymede, are locked in a resonance that keeps their orbit steady. In the asteroid belt, certain resonances with Jupiter create gaps where no asteroids can remain for long. These patterns show how gravity shapes orbits not just randomly, but often with elegant precision. Over billions of years, the solar system became what we see now, a family of planets, moons, asteroids, and comets, each moving along its own path, held in place by the invisible grip of gravity. But even today, the system is still not perfect. Gravity continues to cause small changes. Planets slowly shift their positions, asteroids sometimes break out of their usual paths, and comets dive in from the distant edges of the solar system. Yet compared to the chaos of the early days, the present solar system is like a calm and ordered dance. The story of gravity shaping orbits is not limited to our solar system. When astronomers look out at other stars, they see evidence of similar processes. Many stars are surrounded by disks of dust and gas, just as our Sun once was. In some of these disks, new planets are forming right now, and astronomers can even watch how gravity pulls the material into rings and clears out paths where planets are beginning to orbit. In other systems, they see giant planets that have moved from one part of the disk to another, a process called migration. This shows that gravity does not just shape orbits at the beginning, it continues to shape them for as long as planets exist. One of the most dramatic reminders of gravity's power is seen in the long history of impacts on planets and moons. The craters that cover the moon's surface, the scars on Mercury, and even the marks on Earth's surface are all records of how unstable orbits once brought objects crashing down. Each crater is a memory of a time when a rock or comet was pulled by gravity into a planet's path. While most of these impacts happened in the distant past, a few still happen today. In the year 1994, astronomers watched as a comet called Shoemaker-Levy 9 was torn apart by Jupiter's gravity and then crashed into the giant planet, leaving dark scars in its atmosphere. This event was a dramatic reminder that orbits can still be unstable and that gravity's influence never ends. The stability we now see is the result of billions of years of trial and error, of destruction and creation, of chaos slowly turning into order. It is a story written not in words, but in the paths of the planets, the scars on their surfaces, and the harmony of their motions. It is a story that continues every time we look up at the night sky and see the planets shining among the stars. They are not just distant lights, they are survivors of gravity's great game, held forever in orbit by the sun's unyielding pull.